Good morning and a very warm welcome to the Siemens Research and Innovation Ecosystem Conference. My name is Manuela Ockel. I'm a research assistant and PhD candidate at the Institute for Factory Automation and Production Systematics, and I specialize in the application of additive manufacturing technologies in power electronics, which is why I'll be leading you today through this conference. For this occasion, we gathered several experts in power electronics like Professor Sibylle Dieckerhoff, Professor Dr. Jörg Schulze, and Professor Rolf Hellinger for some very exciting keynotes. We are also going to have a panel discussion about the transformation of power electronics with Judit Klein from Zollhof, with Professor Dr. Nagy, which I'm very excited about. And after a short break, we are going to discuss the different cooperation possibilities for industries like Siemens, because it's not the industry itself, but it's also the cooperation with research and universities and also startups with exciting new ideas. Please keep in mind that this live stream is being broadcasted. You can revisit it anytime. And if you have any questions, feel free to ask them after the keynotes in the live audience. Please wait for the microphone so everyone can hear your question. And for the online audience, you can also ask questions. We have provided a tool, so you have to check all the boxes and provide your information. Don't worry if your question can't be answered. We will provide the answers to you after the event. So without any further ado, I'd like to welcome Dr. Roland Busch, the CEO of Siemens, and Professor Joachim Hornegger, our FAU president, for some opening words.
Joachim, you first.
Sorry for that. There are good days and there are excellent days, and today it's an excellent day for me. And I am very proud that we have today this event that is also combined with two anniversaries, actually. So we have the first year anniversary of our RIE Erlangen-Nuremberg, the ecosystem for research and innovation that is more or less driven by Siemens, FAU, and all our partners in the region. Completely new approach to link people here in the region. And the second reason why it's time for celebration is that we congratulate Siemens. Siemens has its 175th birthday, and that's also a great anniversary. And if we talk about anniversaries, next week FAU will turn 279 years. So tradition and innovation combined in a perfect manner. And for us at FAU, it's also important that we did the shift to RIE, that we do not consider just FAU and the disciplines at FAU and the interdisciplinary collaboration at FAU, but to see the larger context, to see FAU in the ecosystem that is existing here, right in the metropolitan region, where we can collaborate with our partners in a unique manner and strengthen also our activities, our visibility, and also our impact on society and the world. I'm very happy to welcome the important partners of our ecosystem. Of course, Roland Busch, the Siemens CEO, is highly welcome. And we are very impressed that you invest half a day of your valuable time to discuss with us and to support the activities here in the metropolitan region. I'm also welcoming the Fraunhofer Gesellschaft, the Fraunhofer IES, Albert Heuberger is with us, Fraunhofer IASB is with us, Jörg Schulze, who is also hosting us today. We are very grateful and thankful, dear Jörg, that we can use your infrastructure for this event. I'm also happy to welcome the Zollhof members, one of the fastest growing technical incubators in Germany. That's unique and outstanding, and we are very proud. And also Zollhof has an anniversary. The Zollhof will turn 5 years in a few months. And I'm also cordially welcoming the president of the technical University of Applied Sciences, Nuremberg, Technische Hochschule Nuremberg, Niels Oberbeck. Lieber Niels, nice that you are also with us. And ecosystem means to build up a network here in the region, in the metropolitan region, but ecosystem means also to build up the links and strengthen the links to other ecosystems, to broaden the view towards things. So I'm very happy and warmly welcome Professor Dieckerhoff from the Technical University of Berlin here in Erlangen. And we just mentioned that Berlin is so close to the metropolitan region, just 3 hours by train, and the close collaboration is really something that is easy to implement. So, warm welcome. I hope that we will have an exciting day, exciting ideas to discuss, and if I look at all of you, I think we have an inspiring setup here, and that's the perfect starting point for an ecosystem and the improvement of an ecosystem, and I'm pretty sure other regions might be a little jealous about the situation that we currently have here at FAU in Erlangen, in the metropolitan region of Nuremberg. Welcome.
Yeah, very warm welcome from my side too. Indeed, we are celebrating 175 years of Siemens, and in the first year of the research and innovation ecosystem, which is a format which we developed further. Talking about developing over the years, when we draw a conclusion, what did Siemens do over the last 175 years? There's one constant in these 175 years of development, which is the constant of change, of reinventing the company again and again and again. We started with a complete different portfolio. Some elements are still there, but we really reinvented. And this is, I do believe, is that what really makes us different, not just surviving, but really surviving as a strong company, as a technology company over so many years. And the challenge now is, this is the second conclusion which I drew, that the very same generation which is managing the company right now has to do that all over again, with one difference. The challenge is that the speed with which we have to transform and reinvent ourselves is dramatically increasing. Reason is that a combination of digital technologies, and these digital technologies, they roll over all our industries, in combination with fast development of non-digital technologies, like power electronics and the like, plus new business models. If you blend this mix, you will see an explosive mix which really boosts companies, markets with growth rates unseen. This is the point. If you want to survive in that system, you have to be extremely fast. Running fast means developing new ways how to collaborate, and ecosystem is not a new word for describing a collaboration. This is something substantial different. Ecosystems, what they do is they leverage each other, and I'm always saying is rather than taking the same cake and dividing it into more pieces, we create a bigger one. So this is the whole idea about ecosystem, of interlinking ecosystems. You have one at the university, we have one, we are combining it. And in that very same sense, you have to really focus on what you're good at and take partners in your ecosystem who can contribute. And together you just move faster and you can achieve more. And this is the idea behind RIE. The next development step, first year, I think with great success already, and it's just the start. And let me maybe close with an example which explains to you what that means. When we started off about thinking how is the next development step of what we call Industry 4.0, call it Internet of Things. Actually, it's the industrial metaverse. Industrial in the sense it could be the infrastructure metaverse, the mobility metaverse, even the human body metaverse, or human metaverse. When you talk about this industrial metaverse, I was getting in touch with a company called NVIDIA. You might know that. They make GPUs, they do AI, they spend a lot of money on it. And when I met the CEO and I came back to our people, I said, let's bring these guys into our ecosystem, let's partner. And then the feedback from our people first was, oh, we can do photorealistic stuff too. Okay? And I said, on what level? I mean, this is a company, they are dedicated for it. I mean, their whole money they spend in R&D is maybe on this one segment equals the whole money we spent in R&D of the full portfolio of Siemens. So is there any chance to really beat them on photorealistic representations? Maybe not. They have Omniverse, they have the way how they are collecting data and they are merging data and bringing that really in a photorealistic way to life. And they have the GPUs, the hardware. So isn't it meaningful that we combine and they do what they are good at and we do what we are good at? Meaning when NVIDIA is animating a robot, they animate it. It can move, it moves fast, it looks photorealistic. When we bring our competence to it, we're going to simulate it. So that means it doesn't move extremely fast, but it starts swinging if it moves too fast. So bringing physics into this metaverse is the essence. Otherwise, you cannot use it. Otherwise, it's just a game. So bringing these competences together, leveraging each other's ecosystem, the go-to-market, the competence they have, that's something what I believe makes us move much, much faster, creating completely new things, and each company can focus on what we are good at. So let's see, we bring it to life as we speak. We're working on it. We want to do much, much more, starting maybe with small applications, go for a really comprehensive view. Plan is to really make a complete assembly line, a metaverse. It's a start, but we are developing fast. This is the basic idea behind it, and we want to bring, coming back to the universities, they are really a very, very essential element of our ecosystem too. Because every innovation starts with research, with invention, before it finally hits the market as an innovation. And I do believe we have great people on board. We have the most innovative university in Europe.
In Germany. Number 2 in Europe.
No, there's a challenge. There's a challenge. Number two in Europe. Look, and this is an excellent exchange. I appreciate it, and I appreciate also being here today and to listen to what's coming. So I'm very excited. Thank you.
Thank you for your inspiring words. The base of an industrial metaverse is electrification, and one part of electrification is power electronics, which is why we want to do a deep dive into power electronics with Professor Dr. Jörg Schulze, who is the current shareholder of the Institute of Electron Devices, and he's going to talk about the core technology, or one of the core technologies, silicon carbide, and its influence on power electronics and quantum technology. Welcome to the stage.
Yeah, before I become the chairholder of the chair on electron devices of our university, let me stay the head of the ISB, which is your host today. First of all, in the name of my whole team, a warm welcome here at ISB. We hope that you have an exciting day with us. We are very honored to host this little conference here. And yeah, I also want to have a contribution a little bit to our discussion, and that's why they gave me the first keynote. And now I'm jumping back, becoming the chairholder on electron devices, and I was asked to give a little keynote on silicon carbide as a material for power electronics and quantum. And okay, in a keynote, I want to give you some messages, takeaway messages. I hope you learn from that. Even the fact that you're not a semiconductor engineer or semiconductor physicist dealing with the stuff your whole day. My first question I want to answer for you, and this is what I want to achieve at the end of my talk, that you also have an idea what does it mean. If you're talking about silicon carbide, and in the next talk, Sibylle will talk about gallium nitride, the second important material what we call the wide bandgap materials, and obviously there are a little bit more. We are talking about the ultra-wide bandgap materials. I think I only have 20 minutes time. What I can show you is that you know what a wide bandgap material is, why we name it wide bandgap material. For that, let's have a look on an atomic structure here of silicon carbide, and if you look to the whole slide, then you see silicon carbide itself forms individual crystal structures with funny names. So you see here 2H, 4H, 3C means, okay, C means cubic, H means hexagonal, and then you see you have some atomic layers following each other, and the number you see here indicates after which period, more or less, the sequence repeats, and so on and so on. But that's not the important thing. Let's look to the inner structure of all these crystals, and then you see there are two features, and this is more or less true for all relevant semiconductor materials we have. Here in those materials, you see that all these atoms are connected to each other on an atomic scale, and you also see that one atom, so let me fix, for instance, here, look at this yellow atom, which is silicon here in this example, has 4 neighboring carbon atoms, and they are connected to each other by covalent bonds. So, and first of all, if you want to become a semiconductor engineer, you have to understand that you have to bring that covalent bond under control. You have to understand the behavior of that covalent bond, because that is the whole story. So, now the big question is, so what you see here is the so-called stick model, the stick representation of a crystal for what the stick connecting the two atoms or two neighboring atoms stands for. As I already said, the covalent bond, or you know it from maybe school chemistry, the electron pair binding. So, but this is just electromagnetic forces where the electrons are binding to each other. That means that it's not a mechanical stable bond which holds forever. That means if you bring enough energy into that crystal, into that covalent bond, then the bond can break. And if the energy is sufficient enough, then an electron is released to the free space of the crystal. So, and this energy, I will show you now, this energy which is required to break such a covalent bond and to release an electron into the free space, and you see it here from the picture, there's enough free space inside the crystal. That is what we call the bandgap energy, or we are lazy people, we are just saying bandgap. Now, of course, you can ask, okay, where's the band? Yeah, so why we are calling that the bandgap? The answer is relatively simple, because if you would ask a chemist which electrons of the silicon and the carbon are forming these covalent bonds, the chemist would answer, these are the valence electrons, these are the outer electrons of the atom, they are making the connection. So that's why we name in the crystal all the volume where all these covalent bonds are. This is what we call the valence band. And the remaining free space in between, this is because if a carrier is in that space, it can freely travel through the crystal. We name it the conduction band, because here the electron conductivity takes place. So, and then obviously, to release an electron from the valence band, so from the covalent bond, into the free space, this is the conduction band, requires a certain energy. That means, energetically speaking, the valence band must have a gap to the conduction band. That's why we call it the band gap energy, or just the band gap. And obviously we have materials. If we have wide band gap materials, then obviously we also must have low band gap materials and ultra wide band gap materials. So if we transform or translate that back into energy or into strength, that means a wide band gap material is a material where this covalent bond is relatively strong. So that means it requires a certain energy to release an electron from that bond into the conduction band. So, and now the question is why we are dealing with those materials, and why especially silicon carbide, what I'm talking at the moment now, or gallium nitride, Sibylle will talk about in a few minutes, why they are becoming important, because maybe you know our most important material at the moment in semiconductor engineering is the silicon. So, to understand that, I want to give you what I learned from my old master, where I learned semiconductor engineering. I'm saying the following thing. The semiconductor crystal alone is a completely boring structure. If that's the whole story, we would not have an interesting technology out of that. So the material alone is just boring. that we can create fantastic electronic devices out of it comes from the situation that we are able, what we call as the engineers, that we are able to dope the material. That means that we bring other materials inside the crystal, and we have two types of those materials behaving what we say N-type and P-type. And we can locally, and that's the thing behind, locally we are able to bring N-type dopants or P-type dopants locally in the crystal, and all the electronic properties, all the behavior of the device is coming from that dopings. So that's the whole story. So if you're asking now, the crystal structure itself, what is the task of that crystal structure? Two tasks we have. On the one hand side is to take the dopants and to hold them in place and to give enough free volume, because finally we want to have electronic devices. The carriers must run through the crystal from A to B, so it must provide that space that the current can run. That is the only task. For the rest, the semiconductor crystal alone should stay silent, should not interfere with our electronic device itself, so should us not bring in trouble. But if I say that, then obviously the crystal alone can bring us into trouble, mean, under certain circumstances, the crystal is overlaying the effect coming from the dopants, and then our devices are not operational anymore. And here we have three scenarios, and unfortunately, all three scenarios are relevant if you're dealing with power electronics. The question is, okay, how to convince the crystal to disturb the device. Because you learned now, okay, if I bring energy into the crystal, these covalent bonds can break. Three scenarios I want to discuss with you to bring energy into the crystal. One is obviously that you just heat the crystal from outside. Heating the crystal up from outside, or the device or the electronics from outside, means in our language, just bring it in what we call a harsh environment. And here you can just read the slide, then you see different technology areas where electronics, mainly power electronics, is required. And you see here just the environmental temperature you bring the electronics in. So high temperatures, and you see here from 275 degrees C, which is the smallest temperature here, up to 600 degrees C, where our electronics has to run. Just to give you an idea, if your semiconductor material has weaker bonds, and if we want to have numbers, let's take the famous silicon itself. If you go with the silicon material to temperatures above 200 degrees C, then so many covalent bonds inside the crystal are broken and free electrons are released that the whole crystal is overwhelmed by these electrons and the device is not operational anymore. So that means in electronics in such harsh environments and just made from silicon is not doable, physically not doable. That's why we need strong covalent bonds, or materials having strong covalent bonds, that the crystal is not interfering. That is scenario A, harsh environments. Scenario B, now we are coming to power electronics. Power electronics means we want to run big current density through the devices. And you know it, if a current is running through a conductor, then you know it's heating up. This is what we all know from experience. And of course, in such a semiconductor device, if the current densities are high enough, then of course you heat up from inside the crystal, you have exactly the same problem. So if the inner heating is too much, again, you have the interference. And the third thing, again for power electronics is not given just by the fact we want to run high currents and high current densities. We also want to block high voltages, several thousand volts. The problem with the semiconductor is you always have some free carriers in the crystal. And now if you apply a huge voltage, then you have a huge driving force to accelerate these electrons or these carriers. And then you can see what happens if, for instance, such an accelerated carrier is crashing against the bond, then mechanically you can destroy these bonds and release additional electrons. This is what we call the avalanche breakdown of the device. So these are the three scenarios where massively from the crystal carriers are coming and disturbing the electron behavior of the device is not operational anymore. So, and that's why we said, okay, if we want to fabricate power electronic devices which are, for instance, able to work in these harsh environments, which hold or block a huge voltage and can run several amps or kiloamps of current, then obviously we need materials which are just silent from their covalent bonds. And here we are in the wide bandgap area or in the ultra wide bandgap area. And at the moment, silicon carbide and gallium nitride are the most important things. Now, of course, you can state, hey, you are the semiconductor engineer. Okay, I understand the problem. Yeah, okay, now invent something. Do it and create wide bandgap semiconductors. And then I must say, yeah, unfortunately, that is not that easy. And if I, as a researcher, say, okay, that is not that easy, my friends from industry immediately hear, oh, it's getting expensive. So, so that's why. Now, first, if you want to make an semiconductor electronics out of that materials, first of all, you need the crystal by yourself. Yeah, what we call the wafer. So our discs, our semiconductor disc, we use for the chips itself. This is what you have to fabricate first. The first idea, for instance, to fabricate nice silicon carbide crystals is, and you see here the patent coming from the year 1958. So. It's relatively old, but here, and you see it from that nice little picture, so that started at the end of the 1990s, that slowly we had a chance to create such crystals where we can start to play with. But you see how big that crystal at the beginning was. And of course, I don't have the time to explain you all in detail why it is so difficult and why it's then so expensive. But just to give you an idea, if I go back to this slide. So why, for instance, it is much more easier to fabricate a beautiful silicon crystal and compared to a silicon carbide crystal. In a silicon crystal, you just have silicon atoms. You just have to convince nature to put one silicon atom to the next silicon atom to the next silicon atom in all 3 dimensions. It's not that easy, but relatively easy. Here on an atomic scale, look at that picture. You have a silicon atom followed by a carbon, by a silicon, by a carbon, by a silicon in all 3 directions. So like a 3-dimensional chessboard, you have to arrange these atoms on a large scale. And just from that fact, you know that is much more difficult than just to bring silicon together. Just as one fact why it is so difficult. And so, but we started, and that was more or less the starting point, which is on an academic level large enough that we can start to create devices. And that was the time where I more or less started with my PhD. Then so slowly also the development of silicon carbide devices started in the academic research. And the funny thing is, so I started my PhD 25 years ago. So if you would ask the people at that time, okay, when that will be happening? So when we will have silicon carbide technology, then most or less the statement was, oh, no one can say. Maybe in 20 years from now. Keep in mind, that was 25 years from now. And the message was, maybe in 20 years. So, and then of course, and here you see what is the problem, or which problems we had to overcome. Here you just see, just as an impression, a lot of defects inside the crystal. Here you see carbon clustering inside the crystal. We had micropipes, really, you could look through it. So these were the startings to grow large crystals. And that's also a problem with silicon carbide. I have shown you that the crystal orientation can be going in different ways. We call it the polytypes, that in one big crystal, the crystal is growing in all different directions, looking strange. So that was the starting point. But we went better and better and better. And for the years went by, we really made the substrates larger and larger and larger. But the funny thing is, if you still ask the people, okay, when it will come? No one can say. 20 years from now. So we had the feeling that even the years went by, so this in 20 years was permanently pushed in front of us. No, it will come in 20 years. So now let's have a look what really happened. And here you see, and this is the most important thing, and now for an industrial application, or that it starts to become of interest for an industrial application is, okay, how large is the crystal? So, or the diameter of the substrate. And you see it here, so it really started with my PhD time, 2000, that slowly the diameter increased. And now I give you here as a comparison how in the same, or how the development of silicon substrate behaved. And here you see the most important substrates we are using in silicon technology for power electronics is the so-called load zone material. And our biggest diameter is 200 millimeters. We are working with that. And the funny thing is, that picture was a prognosis that we are in the year 2020. And the funny thing is, it will come in 20 years. Yeah? We are in the range of industrial wafer sizes. We can work with that. And now let me give you an information out of the ecosystem, and now I'm jumping back being the ISB head itself. Makes me very proud. We are now having an EU Excel Transform project together with all these industrial partners you see here. And you see here that we have now really the technology to fabricate together with our partners and have the technology on 200 millimeters. So that means, and now the 20 years are over, and if you ask me, okay, when it comes exactly now. And I will show you in a minute that you are more or less in the center of gravity dealing with that technology now. So, and now of course, and this is now the interesting story about, we have now the material, and this is now a very funny thing, we had the silicon technology in the past. So, and we started, let's say, okay, Walter Schottky, you are here in the Schottky Street, already started with silicon works during wartime in the last century. So then you can calculate, okay, how long we are already dealing with silicon-based technology. And this is also important, especially Siemens tried to be on the logic work a little bit. But we as German semiconductor engineers, we are not that logic guys. No? The logic, the computer logic itself, that is more or less the American stuff. That was from the beginning, the American stuff. And we tried a little bit, but to be honest, it stays the American stuff. But with respect to power electronics, semiconductor-based power electronics, Germany is the land who's doing the stuff. Yeah? We invented the most of the time, and we worked all the time on silicon technology. So that means that is now there, and we all have the concepts. We know how the devices are looking like. The only thing is we have now to transform that onto the silicon carbide substrate we have now available. And then, of course, I hope that we will now see, that's my prognosis, we will see now an acceleration of this stuff because we already know what we want to build. Yeah? We don't have to invent that. Yeah? But now we have the substrate. And just to give you an idea, so as immediately as the substrate increased, then you see here more and more companies are coming on the race and using that material. The funny thing is, also in that time, and now industry was jumping on the board, and in the conferences, if you ask, okay, when really it will come, no one can say, 20 years from now. That changed completely as Tesla came on the market, because he was jumping on that technology. And then meanwhile, the situation now is more or less exploding, so that we are now exactly in the time to functionalize this material and to make power electronics in that. And of course, now we have the benefit that we have a wide bandgap material, and I explain to you what does it mean that we are now able to fabricate semiconductor technology or devices for power electronics made from silicon carbide. And also here we, LEB on the one side, my chair, and on the other side our ISB here in Erlangen is of course the center where we now used also our skills to develop more or less now a silicon carbide technology. And most important information, we have now what we call a CMOS technology in silicon carbide available. That means we have complementary transistors we can fabricate, which is the key structures for any circuits, for instance, power electronic circuits, that you have the right transistors. Sibylle will talk about in a minute. And for those guys who are familiar with transistor characteristics, look at those beautiful transistors, and just notice, this is working temperature 500 degrees C. Absolutely beautiful working transistors. And the good thing is, I said, here in Erlangen, so you see again a message from the ecosystem, from our ecosystem here. We are now in a situation, the university, our Fraunhofer institutes, and Albert is also sitting here, our sister institute in Tennenlohe, so two big Fraunhofer institutes in the middle, and our industrial environment, and here of course Siemens is one of the key players. We really have now the whole chain, the whole value chain of silicon carbide. This is now available on an academic research level as well for us, on a prototyping level, which is of interest for our industrial partners. And we also have enough knowledge to give a push also to our industrial partners to say, okay, I want to jump now also on that technology. And not only for the big guys, the Siemens guys or the Bosch guys and so on, also for our medium-sized or small-sized companies, which cannot afford a big semiconductor technology, that we said, hey, we can play that. So we are able. And this is also very important for my president. We are the center to train and educate people on that. So we should use that. And we started with this, and this is also an important message from my side into the ecosystem. We are now also part of the Europractice service itself, that we give that technology to our academic partners and so on. They can buy chip area that we've manufactured, that we use the technology, that others can continue and make their research on that. Last thing, I hope I have 1 more minute. I was asked to say, okay, can you also say something about quantum? Of course I can say something about quantum. Not sure how helpful that is, but let me try. Is there a silicon carbide-based quantum electronics? And the answer is definitely yes. So also in that regard, silicon carbide is one of the most promising materials if you want to jump into quantum electronics. First of all, as a key message, what is the takeaway message of this little subchapter before I come to an end? What is quantum electronics? Immediately we think about quantum computer or the hunt for the quantum computer. And then all of us have in mind, okay, that is some fancy stuff no one really understands. So, but obviously there is a quantum computer out there. Google has something, and I don't really understand what's going on. But maybe it's coming now. Maybe in 20 years from now I will understand how quantum computer works. First important message. Quantum electronics. We are dealing with quantum electronics since the 1970s. And very likely all of you guys already have quantum electronic devices in your pockets. And definitely you don't have a quantum computer in a pocket. Quantum technology and quantum electronics is obviously more than just the quantum computer itself. Because what is quantum electronics? These are, from my perspective, semiconductor device concepts where you just use a quantum mechanical phenomena, like for instance the tunneling effect, which is one of the oldest quantum mechanical effects we trained on. You just use for transistor functionality. That's it. From the outside, the transistor looks similar to an ordinary transistor. Also, the task this transistor, for instance, has to perform is exactly the same like the ordinary classical one, only the concept behind is a quantum mechanical one. This is quantum electronics. So it's not only the quantum computer, and we are already jumping into quantum stuff. For instance, here, if you look our classical scaled transistors, we are looking for our computer technology in, and I just want to draw your attention to this acronym here, and especially to the little T here inside, the heterojunction TFET. The T stands for tunneling. That is a quantum mechanical transistor concept, but from the behavior, it's an ordinary scaled small transistor. The funny thing is, okay, that is for scaled MOSFETs. Now you can say, okay, we are now in a sub-10 nanometer regime in scaled MOSFETs. That here quantum mechanics plays a role, I understand. But to be honest, every transistor concept you develop for small applications or small size applications with respect to gate length, and so you can use for power electronics. Yeah? You just have to make it larger, but the concept is the same. That means you also can work with the tunneling concept, for instance, in power electronics. Just to give you a brief overview how such a tunneling FET works compared to classical MOSFET. In a classical MOSFET, and now you see, and this is the loop back to my opening words, we have the NP-N doping structure forms this beautiful barrier itself so that an electron here cannot go to the other side because of that barrier. If we apply a gate voltage, we crash the barrier, the electron can travel through, the transistors turn on. That's it. In a tunneling FET, we are using a PIN structure, which is an ordinary PIN diode, which is blocking the current very well. And the power electronic guys immediately see the P as in power diode, which is here in behind. And if you now apply a gate voltage, you put a tunneling barrier in between and the electrons are tunneling through. It's a quantum mechanical effect. It's a quantum electronic device. And here exactly we are working on that. And just to give you an idea for what quantum electronics is good for, if you're working now a circuit technology with a classical MOSFET compared with the tunneling FET, the functionality is the same, but you save a tremendous amount of space. You can make it smaller, and use the quantum mechanics just to make it smaller. But the effect itself, or the concept, is just an ordinary transistor. But yes, silicon carbide can be also used for the hunt for the quantum computer. For that, I have to explain you that in 1 minute. I cannot explain you that in a minute. But fortunately, Roland was Roland. Is he already here on the podium? He can maybe explain you that in a minute. The most important information is that what we call a silicon vacancy in silicon carbide. And you know now, we learned a lot about how to make a perfect silicon carbide crystal means without any defects. If you have a wanted defect, silicon vacancy means that you grab out one silicon atom out of the matrix and you just keep the 4 carbon atoms, you have the vacancy. Just as a message, we don't have a chance that you really understand it, just as a takeaway message. This system works as a qubit. This is a programmable, optically and electrically programmable and read out quantum bit. Just the information. And now imagine this is just an ordinary defect inside the silicon carbide matrix. We learned now everything to avoid the defects. Means we are now able to bring them in again. And we already have the technology and also the electronic environment to bring the qubit, for instance, into an electronic chip system. So that's why, of course, that is the starting cell. To create a quantum computer, you need a qubit. That is available in silicon carbide technology. That's why I believe silicon carbide will also play an important role in quantum electronics and in the end for the quantum computation. We hope. So what we now have to learn. So the question was, is it stable? The question is now, yeah, of course. I think once you have fabricated everything and the qubit survives, then it stays stable. But of course, the question is, can we go over the whole manufacturing cycle and the qubit stays exactly there where we have introduced? This is what we now try to find out. Is it diffusing away or do we destroy it? And no one knows exactly. But at the moment, we know we can fabricate those qubits, we can control it, and now we have, in the moment, 3 PhD theses running exactly on that topic to find out, okay, how to bring that into our technology, in our ecosystem we are here. And my time is already running out since minutes. I'm very sorry about that. And I think, yeah, that was my last slide, and I thank you. I thank you very much for your attention.
No problem. It was very interesting. Thank you for your vivid explanation of silicon carbide. I myself learned a lot. Maybe we have time for one short question. We already had one. Maybe there's another one.
Is that stable? Yeah.
If not, then I would like to welcome Professor Dr. Sibylle Dieckerhoff onto the stage for the other part of wide bandgap semiconductors.
Thank you also for being invited here to give some ideas on our work. We are working on, as already mentioned by Jörg Schulze, on GaN power electronics, and I was invited to give some information here and on some developments which we are working on for future devices. In fact, I'm somewhere in between with my knowledge. We are a power electronics group, meaning that I'm not really a device people or kind of people, and I'm also not so close in the application, so we are more or less the interface, I think, which also fits quite nicely into the ramp up of presenters here today. So wide bandgap power electronics, we got the basis already, that's good, so I have something to connect here. In fact, looking in terms of application and systems, wide bandgap like silicon carbide and also gallium nitride, they have these thermal properties, which are advantages. And also the devices we can build, they have the significant advantage that we can make devices with quite low charges, parasitic capacitances of the devices, meaning we can switch to them very quickly. So we can achieve very high switching speeds, and that's one of the major system-related advantages of these devices. At the same time, keeping nicely good on-state properties of power electronic switches, which we operate as switch, and which should have low on-resistance during conducting. This is quite an old figure, but nonetheless it's still true. Comparing silicon carbide with gallium nitride currently, when you look at what is commercially available, on the one hand, the silicon carbide is more for higher power, higher voltages, mainstream still being 1.2 kV devices, and the gallium nitride has more or less actually found its niche at a lower level at 600, 650 volts blocking voltage and power ratings up to a few kilowatts, which is at least going to commercialization. So this is more or less, but at the moment, the difference between these two application areas. And compared to silicon carbide, gallium nitride has the advantage that these are lateral devices with a different structure. Usually they are high electron mobility transistors designed. These are lateral devices, as I said, switching faster than silicon carbide, however, and allowing, due to being lateral devices, allowing monolithic integration. On the other hand, the power level is restricted. And I think that's where we are at the moment. And I would like to just state briefly, at the moment, with gallium nitride, we are, there's no pointer, we are here, it's 2022. This is a market forecast taken from the latest ECPE study, a position paper on power electronics in general. And what we see here is in blue, how the market has developed and is forecasted in the future for silicon carbide. And here the pink and the gray curves, that's what's foreseen for gallium nitride actually. And you see we are not really in the market at the moment, but it's going to increase, however, less expected than the silicon carbide here. And the main application areas at the moment is the lower power level. These are very often mobile power supplies or power supplies for data centers. And also what's currently, there are many developments going to automotive onboard chargers. And there have been some works on PV inverters. So that's more or less the market, the mainstream, I would say. And the question is what's coming next? Unclear. Maybe we can learn later after my presentation. Electric vehicles are often discussed, which might benefit. Maybe also aerospace. We have learned about these harsh environments. Some state-of-the-art, maybe I didn't check my starting time, maybe just briefly, what's the state-of-the-art transistors we have? As I said, it's more smaller powers at the moment, so we find several manufacturers all focusing, or most of them focusing on discrete devices. Some have intelligent drivers included in their housing, Texas Instruments, Navitas. We have companies like Infineon and GaN Systems who more look at normally off transistor switches, which with a focus on good heat dissipation, so pushing it a little to higher powers. And we have some kind of companies who have designed transistors which in their usual state are not turned off, but are switches which are in conducting state, so normally on devices. And to have a so-called normally off characteristic, that's what we like in power electronics. We have a switch that in the normal state it's off, not on. And so to achieve this, there is a little bit more complicated structure called a cascode. So to summarize what we can get in the market now, approximately transistors, 600 volt blocking, resistances during on state, 20 milliohm, maybe a little less, with current ratings up to approximately 60 amps per device. And as I already mentioned, we have these lateral devices. So this is a basic structure for those who are not so familiar maybe with these type of transistors. We have a classical lateral source and drain structure with a gate, sometimes in normally on devices. We don't have a doped gate here, but it's directly on the first material, on the aluminum gallium nitride barrier. And there is a channel formed here in between the aluminum gallium nitride and the gallium nitride. Since for cost reasons, this usually is processed on a silicon substrate, we need a buffer layer to compensate for lattice mismatches. Sometimes people ask for vertical transistors like silicon carbide, so transistors for higher power. There are some works, mainly research works at the moment. There is a company, those who are more working or deeper working in this field will most probably know, the company NextGen, who have already also published some results on so-called vertical transistors, where the current flow is from drain to source through the device, which enables higher voltage, blocking voltages, and increasing the size of the chips, also higher current ratings. There are, as I said, mentioned some works on increasing the voltage level here. So that's state of the art. When you look at the transistor and you operate the transistor, it looks like any other transistor as well. So you have this classical transistor curve between the current and voltage, the IV curve here. What's interesting of this device, you have a reverse conducting capability. So meaning if you control the transistor with a positive voltage and negative, when the current flow should be negative, you can have a symmetric current flow operation in the transistor, which allows you to not need further diodes. That's the same with silicon carbide. Switching these transistors, I already mentioned, they are quite fast. So we usually test these transistors in so-called buck converters. This is the basic topology. It's also the typical topology for most power electronic applications nowadays, a so-called half bridge, where you switch a DC voltage controlling the bottom and the top transistor by inversely switching them on and off. In this so-called clamped inductive switching, you test the current commutation between and the voltage commutation between these two transistors. And we have here some results on a device which has been fabricated by our joint lab partners, the Ferdinand Braun Institute in Berlin. So these are not commercial transistors. We switch these transistors here up to 400 volts, and you see it's happening in a few nanoseconds. So with the gallium nitride transistors, you can achieve a turn-off voltage slew rates of more than 100 volts, sometimes 150 volts per nanosecond or even more. So this is one of the major advantages of these devices. And if you switch fast, you can reduce the losses during switching. So you can achieve higher switching frequencies, which has system advantages comparing reducing system size in the end. One major disadvantage, or still a problem also in some commercial devices, at least those normally off, are the so-called dispersion effects or trapping effects, also known under the name of the dynamic on-state resistance. That means that if you switch the devices from a turn-off state to a turn-on state, and when you come from a high blocking voltage, the resistance during on state is not the same as it should be in steady state, but it's increased. And that depends on the voltage level, on the current that you switch, on the speed at which you switch, and also there is kind of accumulation that's shown here. When you operate this converter in continuous mode, you see that the on resistance here starts at some point, and if you switch over time, the on resistance further increases. There is a temperature effect also included, but not only. So this is to what's going on in the transistor. And that brings me off some current issues of GaN. So it's a nice device on the one hand. On the other hand, there are still some problems for broader market application. One thing is limit with the blocking voltage. Then these charge trapping effects we've seen here with the resistance. Also for the transistor switching, there are some threshold voltage instabilities. So the voltage at which the transistor turns on and turns off might be different. The current rating is limited due to the lateral design. That's also a problem for heat dissipation, which is a problem for the so-called ruggedness. So turning off under faulty conditions, for example. And you need to be very careful when you switch so fast. Your circuits need to be designed very properly. Very few parasitics, very few parasitic inductances, and so on, to really achieve clean switching. I think this, in my opinion, this is nice switching. On the other hand, you might think that there is still some ringing, but I think compared to other solutions, it's quite good what we have been doing here. But of course, this is prone to lead to system instability. So you, of course, need to somehow cope with this oscillations. And there are different approaches, and research is going in all kinds of directions. One thing is going into this layout, packaging, also integration direction. Then the question is maybe are there new materials or modifications to the devices which enables, for example, higher voltages and get rid of this dispersion effects. And the question of system design, of course, stays as well. I would like, looking at the time we are spending here, I would like to focus on some ideas on one point, that is the monolithic integration. And I have an example here. This is a classic topology. So we have here our half bridge, which would produce an output voltage usually pulsed in power electronics to convert, for example, a DC voltage to an AC voltage. There are topologies, 3-level, which make or produce a nicer output voltage, having not only the positive and the negative voltage, but also a zero potential switched to the output. This would be this blue curve here. In average, we have a nice sine wave here by pulsing or by pulsed operation of the converter. And in this topology, the so-called T-type, which is popular, for example, for photovoltaic inverters, we would need a switch that can conduct the current in both directions and can block the voltage in both directions. And nowadays, usually you implement the switch by two discrete transistors, and one advantage might be to try to do it with one transistor. And this is a result. These are some research together with our, as I said, partner, FAU Brown Institute. The straightforward approach would be we just make one transistor and have two gates. And in this transistor, the current can flow in both directions and it can block the voltage in both directions. The advantage compared to discrete devices is we have only half the on-state resistance, so half the losses more or less, compared if we had a transistor operate two transistors instead. That's a nice idea. There are many more applications. Matrix inverters, where you directly convert AC voltage to AC voltage, some power factor correction circuits, three-phase rectifiers, also other multi-level inverter topologies. So there's many, many applications one could think which might benefit from this technology. So there's an idea. So this was a produced switch. And if we look at some of the results, we have measured the IV characteristic, the transistor curves, in blue and in green. That's the transistor operating on the one hand, let's say the transistor in this side, the red one in that direction, and it's more or less symmetric. That's nice. And if we compare it to a single device, so the same device only with one gate, we have very low derating. So the current capability is approximately the same. That's nice. Also, the switching is good and symmetrical. Again, we have tested here the turn on, turn off, and they switch in the same, nearly the same. And as you see here again, like in 5 nanoseconds, we switch 400 volts here. However, one problem we have is that for cost reason, these lateral devices are processed on silicon wafers, which have large sizes. So it's cost efficient, but silicon is semiconducting. So there is something which is called backgating. Backgating means that there is this bulk potential here is like another terminal to the device. And with the voltage at this terminal, you control what's going in the channel. And that's problematic for such a transistor because not as in usual transistors, you can just connect this bottom bulk potential to one of the source nodes. In the end, if you look for more, let's say, easy understanding, you look at the single device. So this is also processed by FBH. We have here just a normally on transistor with a silicon substrate, and we have modified the potentials between bulk and source. And what you see is a derating of the curve when you have a negative potential. So the current in the channel here is controlled by this bulk. And there are ideas how to solve this issue. This is not only an issue for bidirectional switches, but also when you want to integrate, for example, circuits like this basic half-bridge topology. You need some ideas what to do with this varying potential here. One idea is to integrate further electronics in the wafer to switch this potential, for example. Another idea is go to other materials. And there is some work going on, and this is also a cooperation project actually with IASB here in Erlangen, and the FAU Brown Institute and us on developing transistors based on aluminum nitride. In the first step, this aluminum nitride is the so-called buffer that improves the overall transistor characteristics, and we have an isolating substrate here with the silicon carbide, which also gives good thermal properties. And here we don't see this effect. So with these transistors, we could go to integration. And I don't have the monolithic example here, but I have the monolithic bidirectional transistor. But we have designed, or not we, but the Ferdinand Braun Institute, we've just measured it, have designed an integrated half bridge with this technology. And what you see here is that you can solve this issue and that you can get nice switching. And you see a further advantage here with the integration of switches when you can reduce the space you need and the loops and the stray inductances and capacitances in the whole setup, that you can switch a lot faster. The green curve is the monolithic new bridge. The blue curve is switches when you have just two transistors externally connected, and you see that you can switch faster and that you have lower overshoots. This here is the current which is switched, and you see in the green, the monolithic curve, quite a lot lower overshoot. Yeah, that as one example. So lateral devices enable integration. There is a lot of benefit gaining from integration, but you can't just do it with power electronics with high voltage levels. You just can't do it on a silicon wafer. That's more or less the message. I would maybe skip this part here with the gallium oxide, and I would like to conclude or present some other research ideas on the future of these power electronic devices, which are currently followed in a DFG priority program. So I'm the coordinator of the priority program Energy Efficient Power Electronics, GENIUS, which is based on 3,5 nitrides. You see here a lot of projects have been granted within this priority program. It started last year. There's also a group here from FAU in Erlangen, from Professor Witzigmann, which is part of the whole project. We have 18 PIs in total. And the research projects here, we have three different directions. There is one part of groups which concentrate on new materials and devices. So the example I've shown here, that's also something which is further followed in the framework of this research funded by the Deutsche Forschungsgemeinschaft. We have other ideas here. There is the idea on vertical aluminum nitride-based transistors, which is also part of the work in Erlangen. Then we have works within the framework here on so-called power ICs. So how do we drive these transistors? How can we integrate the driving circuit, which we need to switch the transistor, this electronics? That's also one major block. And the last one, interestingly, and that's why I took the other example, there are several projects on bidirectional transistors and their application. And with this, I would like more or less to conclude this one topology. We know already the T-type, and there are other ideas where you can use this integrated transistors. So this is by the University from Kiel. They are working together with Aachen to build also this kind of bidirectional transistors, and they want to use it as isolating switch to design reconfigurable converters. This case, a medium frequency transformer system. And another idea that's also something completely different, a completely different application, are rectifiers. This is followed by University of Paderborn here. They have a system where they want to, a charging system for a high voltage battery, which of course here 400 to 800 volt DC might be a battery on an electric vehicle from the three-phase system. We see here the typical bridge, a diode bridge for rectification, and then with a low frequency, they would implement bidirectional switches and get an optimized current waveform from the grid with their topology that they have proposed here. So different applications maybe showing the benefit if you can reach or achieve systems with higher integration. With this, I would like to conclude. So very brief summary, I wanted to just give an idea on the state of the art and show some research example, and I've focused on this monolithic integration problems. yeah, I didn't show the activities on gallium oxide, but some research projects within our DFG priority program. Thank you.
Thank you very much. Again, maybe one question, if you have any. No, then...
Okay, thanks.
You can ask your questions also in the coffee break, so no worries. Now that we heard about two very central technologies of power electronics, we want to talk about power electronics as a core technology itself. What about its influence on an all-electric society? And therefore, I'd like to welcome Professor Dr. Rolf Hellinger onto the stage.
Thank you. So thank you very much, and thank you, Sibylle, and thank you, Jörg, for setting the stage, so it's perfect. As you already saw, it's difficult for professors to speak less than 90 minutes. Therefore, I try my best to keep in time. Power electronics in industry. Is it a core technology for the all-electric society? This is a question. And I would want to try to give you the answer in the next minutes. So why is power electronics so important for us in our days and will become more important in the future? It's very easy. We see three trends. Renewables for sustainability. We are all aware of that. Electrification for more efficiency, and third, digitalization for productivity, as Roland mentioned. And what we can also see is power electronics is everywhere. We have it in the power generation, we have it in transmission, distribution, and more coming up in stationary battery storage, as well as chargers. We have it in the industrial drives, and we have it in the e-mobility. And what are the drivers? The drivers are, at the moment, believe it or not, the industrial drives. It's the biggest market we have. We will be overtaken latest next year by e-car, and wind and photovoltaic will also come up. So we are on the way to an all-electric society, and we have to balance, to be sustainable, our economy and our environment. So our customers are paying us for function and performance, for productivity, and more for reliable supply chains. So it's not the question if you have the, let's say, fanciest technology. It's a question, can you deliver? On the other hand, we see the resource efficiency, and I'm not talking about energy efficiency. I'm really talking about material. I'm talking about how to develop, or how is a material available. We are also talking about dematerialization. So substitute material by software. And we are talking about circular businesses. So our two levers, from our perspective, power electronics, are modular scalable hardware, small modules, software defined on the one hand, and on the other hand, a robust eco-design. And we have to combine that. So why plays power electronics such an important role for Siemens? As Roland mentioned, markets, branches, business models are changing and in transition. And therefore, this can also be seen here. So, inverter market in industrial applications has nearly doubled in the last 5 years and will double once more in the next 5 years. So it's unbelievable. Next point is, power electronic is nearly in every Siemens application. So we have the manufacturing technology, we have the process industry, we have the smart infrastructure and charging, we have mobility, and we have healthcare. And in every application is power electronics. what we also see, and this is really interesting, hardware is important to win the digital race, believe it or not. And so software is nothing without hardware. And what we can see is that our converters, our power electronics, is the digital access point for power systems. So to collect data, to gain information, and to control the system. And this is true because what we see, new competitors are coming up, and these competitors are the forward integrating semiconductor companies and the backward integrating ICT companies, as well as the internet companies. So the question is now, what can be the role of silicon carbide and gallium nitride in this game? Here you can see our power electronics house with the stack on the left side from the power semiconductor via the power modules, power units, and assembly and joining technology to the application and control and converters, and on top, the data services and business. And what's very interesting is we are very strong in this field as Siemens. This is our playing field. And we are now developing the accelerator, which is a platform combining all the assets we have and building up the metaverse Roland mentioned. And to gain more freedom in this field for design, we go one step deeper in the vertical integration to gain this design freedom we need. And there, wide bandgap semiconductors play a central role. So wide bandgap semiconductors, together with planar assembly and joining technology, together with intelligence in the power units, this is, as Roland said, an explosive mixture. Yeah? And we will here now come up with modular scalable building blocks and bring that in our design for our converters. And how do we do that? And now the research and innovation ecosystems comes into the game. First of all, we learned a lot about the benefits of wide bandgap semiconductors, already mentioned by Jörg, already mentioned by Sibylle. And I tried to let's say, do it a little bit simpler. So there are intrinsic properties of the materials. We have an impact on operation, as we already heard, higher operating temperature, lower losses, reduced recovery time during switching. Therefore, we have reduced cooling demand and high switching frequencies. And this means, as impact for our power system, we get smaller cooling systems, higher efficiency, smaller filters, smaller passive components, and in system, a reduction in weight, size, and material demand, which is great. So how do we do that? We are working on advanced power unit technology, so fast switching silicon carbide power semiconductors, integrating sensors and drivers, standard assembly and joining technology. Here, for example, modules which are available on the market. And on the other hand, we developed further planar and assembly joining technology to increase the reliability and the lifetime. We optimize the system topology, so we are looking on the electromagnetic compatibility and the behavior. We reduce the size of filters and chokes, due to the higher frequency and get higher efficiency. We also look at the DC link, what can we do there, and how can we bring more intelligence inside, and we optimize the modular filters. And this means that we can shrink the inverter in the future. Our prediction is 45% with increased overload capability at the same time, and smaller frame sizes, so our customers are able to buy even smaller frame sizes due to the fact that we have a higher overload capability of our converters. And of course, this will fit to the new grid standards coming up now in 2024. So, and this is really a topic not only done by Siemens, it's a co-creation. It's a co-creation with this environment we are in, together with Fraunhofer, together with the university, and also together with other partners. Yeah? So we leverage the knowledge of the different partners where we can find it. So, and what we do, for example, with PhD students, one example. And be careful, it is a demonstrator, so we are far away from a product, so don't get me wrong, yeah? But what we see is, we did a PhD study, and we built up a converter with GaN. And the GaN devices are 100 and a few volts, so, and everybody said, oh, this is not suitable for industrial applications, this will not work, and what are you doing there? At the end of the day, we tried it. And what we see is there is a huge potential inside. So what we did is we built up a 16 kilowatt unit without fan, with fan, but without heatsink. And we changed also, of course, the switching frequency up to 800 kilohertz from today 4 kilohertz. So this is really a huge step. And here you can see the efficiency. The efficiency is increasing dramatically in the full power, so in the normal power, as well as in the part load power. And this is really great. And what we also see is that we can shrink the system by 85%. We can also shrink the weight by 80%, and we are in the limits of the EMI standards. But, of course, there are several questions to answer. First, reliability. Reliability of the switches and, at the end of the day, of the whole converter. Second, we need, if we want to switch with 800 kilohertz, we need a very, very fast control system here. Yeah? So there are a lot of questions to answer still, but I think it's really a promising topic where we focus on. And by the way, we recruited this guy. Second is the cooling system. As Jörg also mentioned, we want to operate on higher temperatures on the one hand, but we have also the challenge that the devices become smaller and smaller, and so the heat flux density becomes higher. And only to have to show you to compare it, this is the heat flux density of a hot plate. You have it at home, and this is the the heat flux density of a semiconductor. So it's even hotter, yeah, and or has a higher density. And this means we have to do something new. And what we did there is a further PhD thesis here with the FAU on a new kind of cooling system. And what we found out is that we can have a closed-loop cooling system with liquid and vapor two-phase cooling, and this is self-oscillating. So it's oscillating because of you have a cold side and a hot side, and so you don't have to bring in any energy. Yeah? So this is really also great. And what we see here is that the thermal resistance is reduced by 70% compared with bulk copper. And bulk copper is the material we use today. So there are also several areas of application where we think this could be used. So what does it mean now? What are we doing? With our vertical integration topic, we go in a revolution in power electronics. We gain the freedom for integrated product design and manufacturing by this paradigm shift. And what you can see here is, of course, our customers are paying us for functionality and performance, and we increase functionality and performance. So we get higher dynamics, higher robustness, more grid friendliness. On the other hand, higher productivity. So we get more power in and a higher efficiency. And we reduce the environmental footprint, 50% in size and 50% in material use. So, and this is also, of course, highly regarded in our company and outside of our company. So we have we have won several inventor awards. We got the Lean and Green Award in 2021 for our manufacturing line. So we are well on track. And what is the key success? Very simple, co-creation. Co-creation in a cross-functional teams from research to product. So starting with basic research, with education, with applied research, with technology development, with pre-development, with product development, including manufacturing, and bringing all these guys and competences together. This is a success. And at the end of the day, let's rock the future. Thank you.
Thank you very much. As always, are there any questions? Anything from the online audience? Okay, nothing. So that's great because we can head into a first coffee break. There are snacks and coffee outside, and I would ask you to come in about 15 minutes back into the room for the panel discussion. Okay, so welcome back to the break and welcome to our panel discussion about the future transformation of power electronics. And I'd like to welcome our 6 panelists. One of them is Professor Dr. Roland Nagy, if you could come to the stage. Then we have Professor Dr. Albert Heuberger. We have Judit Klein from Zollhof. We have Dr. Peter Friedrichs from Infineon Technologies. Then we have Dr. Sven Baumann from the Electrical and Digital Association, the voice of the semiconductors in the politics. and then we have Andreas Groeger from Siemens. Okay. So since we heard about a lot about the core technologies, semiconductors, silicon carbide and gallium nitride, and we also heard that Professor Jörg Schulze didn't have any time to explain what quantum technology and its role in power electronics is, I would like to give the chance to Professor Nagy to explain briefly what quantum technology is and its role in power electronics.
So thank you very much for this very interesting question. So we have nowadays many different kind of quantum technologies. So we learned for example, today about quantum computing that existing, but there are also other quantum technologies. For example, quantum sensing, what is probably from all quantum technologies the most fast evolved quantum technologies, and it's also that also companies already are using this kind of technologies for trying to implement them in their products. And one of the main questions nowadays is in this kind of technology development for quantum sensing is first reducing the price and integration. And this is actually very demanding, because if someone looks how such a quantum sensor looks nowadays in the research, more or less it's built in an optical table, it's quite big. So it's also very expensive, and this makes it actually quite challenging. And as we learned today, silicon carbide is a very interesting material because it can host a qubit, and we don't have many materials who can host a qubit, so there are only a couple of these materials available for us. And this is actually very interesting for us, because it means that we can use more or less everything what is already developed in silicon carbide, for example, microelectronics, power devices, the full semiconductor industry, of integrating, for example, quantum sensors on a CMOS chip scale. And something that this was not possible before, and silicon carbide is a kind of a new material. It's very famous on one hand, obviously, for power electronics, but on the other hand, it's an ideal material also for quantum application. This combination actually makes silicon carbide very important. And due to this fact, actually, it was not possible before actually realizing integrated quantum sensors. And silicon carbide, due to this kind of industrial knowledge what is already available, gives us the possibility, together with the power electronics knowledge, to integrate a quantum sensor in a CMOS process, reducing the price, reducing the size, and bringing it to the market. So it means power electronics actually very important for us, and the knowledge behind the semiconductor industry is also very important for us, of bringing these kind of quantum technologies to the market. So this is actually why there's a strong impact for us in this field.
You mentioned bringing to the market. How far along is it? Is it already applied, I don't know, at Siemens or other industries, or is it at the moment heavily relying on research?
Very, very interesting question. So, I mean, let's talk about different kind of quantum technologies, for example, quantum computing. So if we look nowadays, where's the main research in quantum computing? Basically, it's not anymore in the academic world, right? So, for example, IBM, where I was working before, actually spending billions on building a quantum computer. We have Microsoft actually was spending billions of building a quantum computer. So, I mean, this kind of development and research nowadays for quantum computing, for example, is more or less strongly focused on industrial cases. Another technology, quantum sensing. So we have in Germany many startups. We have in Germany many bigger companies actually who are already focusing on quantum sensing. They are trying to integrate quantum sensors in their products, are trying to use quantum sensors actually of building new devices. So it means quantum sensing is also something, probably even the more fastest evolved quantum technology, what is already on the step actually for the application in the market. It behaves a little bit different actually for quantum communication and simulation. I guess these technologies actually are still in the development. It will take a couple of years. But on the other hand, we have already technologies what are already in the industry actually, and we are looking actually to bring it to the market for solving problems.
Okay, thank you. So we can use silicon carbide. It's not only silicon carbide as a semiconductor material, but it's everything around the semiconductor. So we have chip design, we have interconnections, etc. And I want to ask Dr. Albert Heuberger, what are the challenges? Because silicon carbide is not an easy material to produce, and it's not easy on the materials around the semiconductor.
Yeah, chip design is a complementary capability and technology, which is extremely important also for the power for power electronics, and in general there is three main implications on the as it comes down to chip design. First is that chip design is the enabling capability to bring the innovation into the electronics and hardware-related realm. Yeah, so it's the concepts, it's the software, it's the ideas which are going through chip design into the products. Yeah, and as long as we can make sure that our ideas can be implemented through chip design, so we are able to innovate. And so if this capability would go away, then a lot of the innovation capability would also go away. So this is key to the innovation process as a whole. And secondly, also the chip design is not only about going down to 5 nanometer nodes. There's a lot of aspects in chip design which need advance in research, in the methods, and in the capabilities. For example, in analog mixed signal, in power, in physical design, in the hetero integration, and so this all goes together in this in the methods we need to create future power electronic systems. It's not only that the power device itself, it's also the surrounding control logic, and we heard that we are up to 800 kilohertz switching frequencies. So this calls for advanced digital chip design capabilities. And thirdly, chip design is something which cannot be scaled up in an industrial production scale. It's about humans. It's about people. It's about brains, and this is the education of our own talents, and also bringing in as many talents from international as best as we can. This will be one of our main challenges in the future. And so, and there is also as I may add, there is also a strong activity ongoing and planned also in Bavaria on national level to increase chip design and also try supporting and facilitating talent education for the industry.
Okay.
And so, of course, this ecosystem and the interworking between university and extra university research industry is key. So that's why this ecosystem-based approach is so important and helpful.
Okay, so you already heard the challenges. It's all about the brains. You can scale it. Maybe Dr. Sven Baumann, you are deeply involved into the politics. Maybe do you know how these challenges are addressed? What are possibilities to increase the brain power in order to have the technical advantages we have here in Germany?
For introduction, I think to speak with the politicians at the moment, because the microelectronics or the semiconductor industry is in the focus on the whole world. It's a political tool now between different political systems, and it plays a very big role in the daily politic discussions on the whole world. Therefore, we have to all politicians have to understand how the microelectronic or semiconductor industry really works, because it's one of the most complex supply chains we know on the world. Because the semiconductor industry is not a regional industry. All of the manufacturers of semiconductors are working from all over the world. They have facilities and so on in all regions. And therefore, we are speaking, I'm speaking every day with the semiconductor industry, because I'm supporting the semiconductor industry, all the semiconductor companies which are active in Germany and Europe. And we say a semiconductor chip is turning around the world for 2.5 times from starting production or the manufacturing up to bringing into the application. And there are 3 main value chain steps. The first one is IP. That means development and designing chips. Therefore, you need only software and computer. Then the really expensive part or second step is the manufacturing, the producing chips. That means to insert a wafer into a wafer, and so-called wafer fab, and it's named front end. And the product is only a wafer with a lot of structures, with a lot of chips on it. And then the third step is assembly, test, and packaging. And all these steps are all over the world. A lot of companies are only specialized for one of the steps. For example, the biggest player in the microelectronic industry, Qualcomm, Apple, and so on, they have no fab. They don't they make no manufacturing by itself. They have so-called foundries. You know the discussion of TSMC now. The politicians now discuss TSMC manufactures a lot of chips. They have the IP for the processing of chips, but TSMC have no knowledge, or not the core knowledge is to develop chips. It's a completely different way of working. And therefore, we have to think about all these steps. And one of the steps is really, truly to develop chips. Actually, the situation is that every second chip is manufactured, is designed and developed by a United States of America company. Every second chip is branded with the name of an American semiconductor company. And
are there any, do we want to increase the number or decrease the US number? Is it possible for us? Is it a goal?
America, missed. Sorry.
It's only water.
At the moment, America discusses or presents a so-called US Chips and Science Act, and they spend money, public money, 53 money for only the second part of the production of the value chain for manufacturing for fabs, $170 billion for the chip design and chip development. Not really, but it's too difficult to explain. It's a little. It's not the whole amount of $170 billion, and I think $22 billion for tax subsidies for tax. And the European Commission or Europe discusses says in the last years, we are investing the most public money in R&D and I, also innovation. And the programs, Horizons programs of the European Commission is about $100 billion. At the moment, it's nearly the same, dollar or euro. In the last years, we are the global player, biggest player of spending public money into R&D and I. And now, at the moment, the biggest one who designed and developed the biggest amount of chips, every second chip, they spend on top of the actual programs which are running, $170 billion. I think we have to think about the United States is our big brother, but if we are thinking about technological sovereignty or supply chain resilience, we have to remark, or we have to discuss about it with the politicians if we will maintain our actual share of market in fabs. It's nearly 8.5% at now of the global in Europe, and IP it's also a little bit less than 10%.
Okay.
To maintain these nearly 10%, we have to spend more money than actual we are planning or our politicians are planning.
Okay.
Otherwise, we will not belong to the last 7 countries, states in the world, which can manufacturing semiconductors. There are 200 countries on this planet. We have nearly 70 industry countries, and only 6 of these countries are able to make semiconductors. All others are unilateral dependence on these 7 countries.
Okay, so for me, usually, this sounds like a huge investment. For me, usually less complicated means also in the end a little bit less money. So are there any possibilities to shorten or to make the supply chain easier? Maybe Andreas Groeger or Dr. Peter Friedrichs, do you have any ideas, or are there any ideas in the industry to shorten the supply chain, or is it even useful, possible to shorten the supply chain?
So as we already heard, it's a very complex system. It's divided all over the world. So I think from a Siemens side, we do our best to solve this problem. What I think is really important, what we discussed before, that design competence is one of our biggest topic in here, because there's manufacturing and there's design competence. And from the design competence, we have internal teams at Siemens as other companies also. There's great design competence also in the region here, also Erlangen, Munich area, also the big companies. But it's hard to do, basically. So it's all homegrown. It's hard to tap into, also from a startup perspective, because there must be the tools, there must be all the qualification processes and stuff like that. And it's also a lot of US-based design IP and everything around it. So you have their Cadence, you have Synopsys, but luckily we have Siemens EDA. And so this is the big thing, basically, to tap into this market, to supply also with our tools and set up design houses in the future, to get a little bit more out of this discussion. And there comes topics like RISC-V in. We discussed about that. And I think that's the way to go.
Okay, so you mentioned it's very difficult for startups, especially in chip design, to tap into the huge knowledge a company like Siemens has. But there have to be new ideas which startups create. Are there any ideas? Do you know any startups who are specifically focusing on power electronics and chip design, or is it too complicated at the moment to bring startups into the system?
So, as we heard today, power electronics is everywhere. Obviously, we have a lot of startups that we just categorize as hardware startups, right? Because that is what we talk about. And of course, we do work with hardware startups as well, but the numbers are relatively low. So we supported in the last 5 years more than 80 startups, and we have a 10% share of hardware among these startups. And they are mostly as well software-driven hardware solutions as well, as we heard it before. It's on the one hand, because of the complexity and the issues around the supply chain, the value chain, it's actually a gold mine for startups, because there is so many opportunities there to fix things, to improve things. But it's not without the hurdles that we heard before. How to start there is relatively difficult, and it's on several levels, it's very difficult. It's on the one hand about getting the financing, because this is really expensive to start. So what do startups usually do there? Most of them try to get venture capital, but if it's too early, then it's too risky as well for venture capitalists to get into the space. So this is where ecosystems like this one comes into play, because innovation and invention happens here. So these are great partnerships. They're spin-offs where it's about commercializing that given technology and bringing it out on the market. Also maybe a bit independent of the really big structures that these companies have, in order to enable exploration and not just execution. On the other hand, the state, Europe, Germany, and all these powers are very important here. So there are a lot of subsidies, there are a lot of funding programs available for the startups. They don't have to give up shares, which is very important for them. And then we actually have several startups in our ecosystem who are bootstrapping, which means that they actually get funds from other activities in order to build up their scalable business model. And basically, most of the time they launch engineering offices, so they provide services around the competencies they have in their teams to get some of the funding, and then they reinvest that money in order to develop their own products that later on they want to bring on the market. So it's not trivial, I would say, but I think it's so important that we have the talent here, we have the knowledge here, and we have also crazy but very motivated and brave people to start out.
I think so too. You wanted to say something?
Just might add that, of course, startups in microelectronics is possible, and Intel also started as a startup sometime, yeah. And but there are very specific conditions how these can come into work and grow. Yeah? So one thing is that it's you have a lot of cost in using tools and expertise, and you need sometimes a very long. It's a very long-term business, yeah? And sometimes it depends on the model. It can take 5 or 7 years until from IP invention something substantial flow of revenues come back. So, but it's worthwhile, and there are tools and support structures available already in place. For example, chips. It was the Eurochip or Europractice system where IASB offers a technology. For example, at our institute here in Tenerife, we are the European hub for Europractice for the academic world, and also we do the small volume business for global foundries and so on. So this is, of course, there are methods and tools available which are already in place. We will enhance them. Hopefully next year there might be a Bavarian Chip Design Center, and this will specifically aim in lowering the entry threshold for microelectronics design, for the design tool environment, for the Europractice support, IP support, RISC-V will play a role, and so on. So this is being taken up already in from Bavarian government, hopefully. So this is not approved by parliament budget already still, but I think we can be optimistic that at least at this regional level something will happen. Of course, we will need a lot more activities and a really different scale in funding for these activities, as you pointed out. So this is what Europe is paying and doing is really 1 or 2 orders of magnitude below what is really necessary.
So we already know that there are cooperation possibilities with Siemens and startups. Maybe how is the strategy at Infineon? Do you have examples of cooperation with new startups who had great ideas, or do you focus on more investments into your own research, because we need huge investments and it's usually easier to invest it into your own company?
Yeah, definitely startups have an important role also for us at Infineon. Actually, in I think 5 days from today, we have our startup night, where we always invite also startups to make their pitch. We invested in startups, we integrated them over the last years. Where we see the role, basically startups do things where we typically as a big company are not, let's say, jumping far enough in our innovation. So internal innovation is typically somehow a break by controllers asking for a business case, to be very frank, or then we have those gray-haired guys like me telling we did it 20 years ago, it doesn't work. So there are some mental hurdles always available, and startups think differently. So they really are open for crazy things, and this is a benefit we can take from them, that we then get technologies, so not just software but also real hardware into the company, which we would never do by ourselves. I personally also had the pleasure to be a part of a startup integration. So 4 years ago we built a startup in Dresden, and the technology is great, but the challenge, of course, which is in place, is to get from a startup kind of demonstration into something commercial. This can all be managed, but the people being involved, especially coming from the startups, they for years had a different operating mode, and this is really a big topic also for companies or big companies, especially trying to integrate startups, that there's something, at least in the first phase, like in cultural clash, and we need to be very careful not to lose those people with their innovative thinking, not to ground them in the first days with procedures and processes. So that's a learning what we have made, we try also to create some should I say, experience from that also for further steps. But I think this is the biggest hurdle, especially in big companies, when it comes to cooperating with startups. So the benefit can be huge, but there's a very high activation energy from taking the innovation in the company and merging it with internal requirements regarding production capabilities, etc. But again, so absolutely essential to have startups, also in hardware, not just in software. I think that it seems pretty easy for software, but hardware, much bigger investments. And one experience also I would like to share here is, if somehow possible, if it comes to the financing of the startups, so to a certain extent the financing is done in a way that really the innovation is pushed. Unfortunately, then comes a phase where basically investors look for the exit to make money. And this phase then somehow slows down the innovation also in the startups, because those guys also only think in the exit scenarios. So we need to grab the right phase in the startup innovation to neglect this or avoid a little bit this last phase, because there's no real innovation taking place in this last phase, because they just work on making the bride nice for the investor. So this we experienced a couple of times, and therefore the financing structures, if we can do anything also with politics, that maybe, let's say, more relaxed funds are available for those startups, that they really can work on the innovation and are not forced to look only on some payback scenarios of the investors. That would really help also from our point of view. Of course, also we as an industry should take care for that, not just politics.
Sounds reasonable, but I think it's very difficult to implement this kind of mindset into a big company.
I know.
Talking about crazy ideas, quantum for me is a crazy idea because I'm trying to understand it. Is quantum technology, quantum sensors, quantum computing not so much, but quantum communication something startups can tap into, or is it, or could be the possibility out of research to create a startup? Maybe is there already a startup which focuses on quantum in some kind of way? Are there any ideas?
In Australia, we did have an application actually last year. So there are different hubs in the world, and I don't think this is a topic that one country can or will solve. So it's all about collaboration again on the global scale. So there are startups, and I was just recently in Copenhagen in Denmark, and it was a startup event also, and there were some startups focusing on quantum. But obviously, until the actual technology, the research and everything comes together to get there, as we heard, there are billions invested in this topic. So I think the momentum is there, and I'm just really curious who will crack the case first.
Me too. Where do you see the highest potential for a startup? Which part of the quantum technologies?
So I believe it's a kind of a broad question, because if I look at these startup companies, for example, Quantum Brilliance, what is a startup from Australia, what is 50% in Australia, 50% in Germany, it's more or less what they're doing. So in general, they're obviously realizing some technology, but the realization of this technology is separated in different parts. For example, the quantum interface electronics. So electronics actually what demands actually to control a qubit, what can read out a qubit and so on. This actually is what many startups doing. So many people probably don't even think that this is somehow related to quantum technologies, but is kind of a key requirement that we can control a qubit, that we can read out a qubit. So also quantum interface electronics is part what many startups are doing nowadays. So this is actually one thing. The other point is I believe that most of the startups right now in the field of quantum computing, and in the field of quantum computing, they are distributed on one hand in software development. So they're developing different kind of software algorithms. They are checking for new kind of algorithms where I can use a quantum computer, for example. Especially also bigger companies are doing this because they want to be prepared actually when a quantum computer comes into the game. The other part is technology development. So we have many smaller companies actually what are trying to build a quantum computer, and they are actually quite fast even. So they are already going to the 100 qubits with different kind of technologies. Also in Germany, there are a couple of companies, also in Austria, for example. And the last part, actually, as I mentioned at the beginning, is the electronics. So there are also companies actually who are focusing on this part. And here comes actually the semiconductor industry into the game. So without the semiconductor industry, this kind of quantum technology development will not work out, because we can't put an optical table somewhere and say, okay, this is a technology what we can sell. It needs to be integrated. It needs to be functional. It needs to fit to the demands what quantum technology have. So it means all around we have different kind of fields actually where startups are working on it. And from my perspective, all of these fields are very potential actually. And I guess there's a lot of potential of doing, at the end of the day here, money in these fields.
Okay. So thank you very much. Our time is unfortunately over. Maybe are there any questions from the audience? Because we have, I think, very interesting people here. Otherwise, yeah? Yeah.
Obviously, the United States is spending, I think, 200 billion, and Europe spends also. And the whole thing is about kind of reverting a dependency which we have on TSMC, where most of the high power chips are coming from. How long will it take until this whole thing is more balanced? Is 5 years good enough? Is the money good enough? And is it just money, or is it also about people?
Yes. There are a lot of difficulties to gain the target of the European Commission of, for example, 20% of the global production capacities in Europe. Actually, we are at 8%. We have to spend a lot of money in production capacities, but we hear it's also very important to spend human resources and spend money into development and designing chips. In the actual situation, we are not unilateral dependent on any other country of the world now, because we are the global leader in power semiconductors. We are here in Europe global leader of MEMS, and we are global leader of analog mixed signal semiconductors. But we have to look at the actual political situation. For example, the United States are investing a lot of money into the semiconductor industry because they understand in the last 2 years, because semiconductors are not enough on the world for all which needs it for their products. But not only America is investing a lot of money, also China is investing big amounts of money into the semiconductor industry. Taiwan is spending a lot of money. South Korea is spending a lot of money into the semiconductor industry. And like I said before, there are actually only 7 countries, if you count the European Union as one country. There are only 7 countries which are dealing or which can manufacturing or developing semiconductors on the whole earth. And when we will play a role for the next decade or for the next decades, then we have to spend a lot of money, but not only in production, not only in developing. We have, like you said, we have to develop a lot of money and for time, because here are a lot of students. I saw 2 weeks ago a study of IFOR. Last year, electro engineers, there were from 100 positions, there were only 55% the companies get somebody for the position. In 2030, they calculate or make a prognosis. Now listen clearly, 86% will stay vacant because we have not enough human power for it. And when we think about what we are in Europe, We have no diamonds in the earth. We have no cobalt in the earth. We have no lithium that we can take off. We are engineers. We are a region of engineers. We have to bring our brain into products, our ideas in innovations. And when we have no people for it, it will be very dangerous for Europe. But the problem of the human resources is not only a European problem. The Chinese also are looking for a lot of people in the semiconductor industry. The United States also. The human resources is a global competition. In the next years, it will be a big competition between the regions for people who are working for the semiconductor industry.
So, for this question, how much money will it take, and how long will it take? So, my personal guess is that if we invested 10 times what we are doing, or even 50 times what we are doing here in Europe, this will be enough not to fall behind even more, as we are already behind. So, keeping up and getting up to 20% production capability. This is, of course, an ambitious political moonshot goal, but it's going to be very, very hard to come even close.
But without this moonshot target, they will not react in a positive manner that we will participate with subsidies and so on. Yeah. They have to have dreams like that, because otherwise the money will much more less.
Sure.
And then it's nothing for us.
It's a political game at the end of the day. Yeah.
I'm making this job since 15 years, and in the last only in the last 2 years they are listening really to us.
Sure.
In the years before, they are not interested in semiconductors, or it's a technology. What?
Yeah, but the question is also how to accelerate it now, basically. Yeah. And for this, nobody can do it by their own. So you need bigger kind of ecosystems,
yes.
And you have to have access to tools. We spoke a lot about this, because you have access to digital tools, then you can look at the market, if the market scales, and you have the tools, then you can do a startup. We have seen this in GaN. So they came up with startup technology out of Santa Barbara, LED technology. And the biggest, at the moment, companies who are using GaN is Apple for their chargers. And the second one is PV. They're coming up with micro PV inverters, and there are big markets around. And so these are the drivers, and they came from the startups, and the universities enabled this. So I think we're on the right spot here. Rolf did a great job with power electronics in the company, open up now. And we see the same story now with digital also, and with the processors and the overall design, because we need it. We see integration coming up in the future, also moving digital more to power electronics, do more mixed, and system in package and stuff like that. Because when you do modular chunks, you can do other systems than now at the moment. Now we have like different systems on sizes, depends on the module sizes, depends on cooling. In the future you have chunks and combine this and do modular stuff more. So it's a complete new thinking. For this, digital design tool is key. Luckily we have something from Siemens for that in the future. But now the thing is also how to get the students access to that. This is the key now at the moment. So get access to our tools, do SaaS model, whatever, the people can pay it with a credit card, and not, that somebody from Siemens have to step by and show them what tools we have. I think this is the key now to accelerate also the bigger community around. And then we have Fraunhofer and our university friends to give also access to their labs and stuff like that, because to run this, it costs a lot of money, and nobody can afford this as a startup or a student. And I think that's the way to go for the future.
Okay, so thank you very much. Unfortunately, we are out of time. We will have a short coffee break, so you can ask any questions you have to the panelists. I thank you very much. I think it was very interesting and very insightful. And I'm also very happy about the startup pitches we are going to have after the coffee break. Okay, So in the last hours, we heard a lot about power electronics and the technology itself, and we already started to discuss in the panel discussion the role of startups and cooperation models in the ecosystem. And that's why I'm very excited about the upcoming pitches. We have several startups here today, which will be moderated by Judit Klein. And we are also going to start with the FAU-Siemens cooperation presented to you by Mirjam Mantel and Sebastian Reitelshöfer. Thank you.
So hello, for me it's like coming home, seeing all this switching trends and pictures and so on. But let's now widen the scope to production topics and robotics at least, yeah. So my name is Mirjam Mantel from Siemens Technology and the CCT and TF Power Electronics. And together with Sebastian Reitelshöfer from FAU-Fabs, I want to present you our cooperation topic, Intelligent Hard and Software Enabling Compliant Mechatronics. So let's explore how we can drive the future of production. There are a lot of technology trends in production which are happening right now. Yeah, the future of production is self-organizing, is autonomous. We can see already, of course, robots, HVs, AMRs, and collaborative robotics. So Siemens human-machine collaboration is an upcoming topic. This is all driven by the demand for more flexibility in production, and it comes with a trend for full data transparency and industrial IoT, for more efficient production processes, for less failure rates, and at least also for manage all the sustainability aspects here. This leads me directly to our global challenges, which are mainly caused by our global greenhouse gas emissions. And just let's have a look at these numbers. Our technologies can really help to decarbonize the relevant sectors. Yeah. Industry is at least responsible for nearly 1/3 of worldwide greenhouse gas emissions. And all the technology trends I just mentioned before, of course, they're very important. The future of production needs to be, first of all, sustainable. Yeah. This is already part of our strategy. So motivated by our degree program. Degree stands for decarbonization, ethics, governance, resource efficiency, equity, and employability. We want to address, in this context, decarbonization and resource efficiency. So we want to support the 1.5 degrees Celsius target to fight global warming, and we want to achieve circularity and dematerialization. And today we're talking about power electronics and electronics. So the drivetrain technologies can really have a big impact on these targets, yeah? And this is directly related to innovation in the fields of power electronics, and smart systems. And we cannot achieve that alone. We need an ecosystem, we need partnerships with our customers, with other companies, and with you, our research and innovation ecosystem here. So together we have the right technologies to drive a sustainable future of production. Together we can drive innovations towards the application. Together we can then tackle the global challenges as well as the challenges of our customers. So now let's have a deeper look into one of these partnerships, FABs cross Siemens, and our topic, Intelligent Hard and Software Enabling Compliant Mechatronics. This is not directly a sustainability topic. Yeah, we are here addressing seamless human-machine collaboration, and also, and this is somehow related to sustainability, systems with high dynamics and high energy efficiency. And how did that partnership look like? Or does look like? Yeah. For the last 3 years, or more than 3 years, we had 2 PhD students working on this topic together. One in my group, Mechatronics Systems and System Integration at Siemens Technology in Munich. It is Takeru Nomoto, and he is here in the room today and also can show you his results in the poster session later. And the second student, Jonas Walter, in Sebastian's group at FAU-Fabs. And they're really working on a daily basis together and developing the basic technology of this topic. And now we are partners in an SNG project where we bring this technology into an application. But this we will explain later. Why are we working on that topic? So safety is an important issue for human-machine collaboration, of course. And nowadays, the systems, the HGVs, the cobots, if they're really working efficiently, we need to stop if there is something in their environment which is not a human and so on. And we are really looking for systems which are collision tolerant instead of collision avoidant, or combining both. We are looking for systems with lower mass and inertia. And for us, it is interesting how to control and how to integrate innovative robotics into this industrial automation ecosystem. And based on this, we decided to have a deeper look into one bio-inspired technology, tendon-driven systems. So academic research shows a high potential of these kind of systems. They are working like our muscles, somehow. And they haven't made the leap to industrial applications right now. So we wanted to understand why, what is missing, how we can leverage the potential of these technologies. They do have a lot of big advantages. We have really a low mass and inertia, so high acceleration and deceleration, which leads to a higher energy efficiency, and it also leads to a safer physical contact. They have a controllable mechanical stiffness, so they are robust against collision, and they are shock absorbent. And this is something which is really known to industrial applications. It's a parallel kinematics, and this comes normally with a high payload capability and broad design freedom. So this just as a short teaser, and now I will hand over to you, Sebastian, and ask you to share your insights.
Yeah, thank you, Mirjam. Switching the slide master, same project, so we were very, very happy to be asked years ago to, together with you, further develop mechatronics and robotics, and we had an ongoing, fascinating project. I'm very happy I heard it numerous times today. In robotics, over the last years, it was always AI, and it was kind of mixed up. And I'm very happy to hear that people are also thinking in hardware, because robotics is hardware and software. Mechatronics is hardware and software combined. And I can start with a short motivation, trying to emphasize on the project we had and we are planning. So for robotics, for nearly 50, 60 years, it was clear that robots are mechanical engineering. They are made of steel, they are hard, heavy, robust, and precise, and they will find numerous applications today and in future by being so. And then there was a small paradigm shift that more and more grew attention, namely soft robotics. So people were all of a sudden fascinated by the idea that the robot is not longer a steel thing, heavy, but it could be soft, compliant. And this is very useful because you can do fascinating things with compliant kinematics. For instance, grasping things. There is mechanical intelligence inside the system because it easily adapts to unknown uncertainties in its environment. Like I'm grasping something from the table, my fingers bend, and without precise sensory information, I'm able to grasp something. But the pendulum swung a little bit. Of course, it was new. People were very fascinated. And there were people saying that, okay, now robots must be completely soft. Everything must be soft. The battery must be soft. The computing must be soft. And probably the answer is a little bit in between. I always use the picture of when it shows up the Humboldt Kalmar, because it has been an archetype for many fascinating soft robotic papers with its overdefined, hyper-redundant tentacles to catch prey. But with its beak, it has the hardest material known in the animal kingdom. So nature often combines soft and rigid systems to realize perfect fitting to certain applications. And this is somehow our project also started. We tried to combine soft and rigid elements, and the outcome of this project over the last 3 years we were invited was a hand wrist where we had rigid components, and we had flexible tendons. And of course, there is really so much mathematics inside, but what can you do with such a system? First of all, you can do things you shouldn't normally do with a robot. So you can have impulsive loads in the system, and you can use the system, for instance, for hammering. If you use a robot that has a harmonic gear drive, it can start hammering, but after several minutes, it will stop to operate. With this combination of soft and rigid, you can do fascinating things. This was the idea behind this project, and now we are very happy to have an ongoing new project, and we are part of a large project that was initiated by the Fraunhofer IES, and makes a nice close of the circle. It's about resource efficiency, and we can be together with partners from the recycling industry, be project partners in there to use this approach of tendon-driven robots to improve automation in recycling. So the use case is that in recycling in Germany, it's the gelbe Sack. So it's plastic waste, and it's running on a conveyor belt. And at the moment, people are standing at this conveyor belt and removing objects that shouldn't be in the later processes. And if you will use a classical robotic system to remove parts like a bicycle, or it could be even a wheel of a car, probably the robot will hit exactly the bicycle and go to emergency stop. Okay, let's use soft systems. They will probably slip around the object, but the classical pneumatic systems are far too weak. But by using those tendon-driven systems, we can switch between soft when it's needed, and then we can firmly grip and remove stuff. And we are able to combine this with AI to make it really usable, with digital twins to simulate it. And it's a very nice example to have a common research on groundbreaking robotics or mechatronics. So that was a short presentation of our collaboration, and thank you for your kind attention.
Are there any questions, or are there questions from the online audience? Doesn't seem like it. So thank you very much. It was very interesting. And I would now like to welcome Judit Klein, because she's going to present all the interesting startup pitches we are going to have. Das kannst du den Startup-Landern geben.
It's going to happen now in the next couple of minutes. I'm going to present 3 startups to you. Each of them will have 10 minutes to pitch their projects to you, and then there is a 5-minute Q&A. I, of course, prepared some questions, but I would invite you and would be very happy if you also join me asking interesting questions from the startups, because asking question means you are interested. So I think it's important as well to show our interest and respect to the startups who are presenting here today. And with that, I would like to welcome the team of Evolonic on stage. This is a startup which is doing a lot of exciting things around flying and drones. It's a project from FAU and Fraunhofer Institute as well. So I think this is the right audience to see how far you are and what have you achieved so far. That's your presenter. The stage is yours.
Okay, it's working? Yeah, okay. My name is Adrian Sauer. I'm head of Evolonic. It's a student team and research project of the FAU. We have a strong cooperation with the Fraunhofer ISB. And how large is our team? We are 25 students right now, up to 30 team members. And we focus on long-distance drones. from the development until to the testing, to competition flights. That's our past right now. We had it until we started 2020. And 2022, we won the international flying competition in Hamburg. It's a flying and construction competition against teams from all over the world: Australia, Mexico, Serbia, China, Australia, and also the TU Munich, for example, or the Heuberger University. And we took first place 2 times in a row, so we're quite successful in this kind of area. And also, we won first place in the FAU Startup Demo Day, located at Zollhof. So we presented our business plan quite well, which I'm gonna introduce to you now. So, what is, beside our competition, what do? We want to attack the serious problem of forest fires. Everyone knows the climate change is a serious problem. It's getting worse and worse. We have a significant influence on the climate change just by the emission of CO2. For example, we have 730,000 tons of CO2 emissions just in Germany. On European level, there's right now no data available, but you can assume it's getting more. We have in Europe 2,580 fires this year. But it's not just like in places like Italy, Spain, Greece. It's also right in front of our houses. This is Tenlower Forest in July this year. This is video footage by our own drone, which we did in cooperation with the Fire Brigade Erlangen. And as you can see here, it starts, this is the very beginning. It starts as a small fire from far. It's just like someone maybe having a barbecue. But it suddenly gets into a serious problem, and Fire Brigade fortunately was early enough to distinguish it. But we need really well-working systems to detect the fire in early stages. That's when we come into play. We have our platform. We have our long-distance drone, which is not linked to any infrastructure. We can take off vertically in any environment, and we attach sensors. We have a RGB camera, which is the first stage of detection. We want to detect smoke. In the second stage, we have a thermal camera and redundant sensors, such as pyrolytic sensors and carbon monoxide sensors, just to confirm it's a fire or it's just dust or any other particles in the air. It might be wrong detection, but we need to make sure it's a fire, and we need to alarm the fire brigade. We don't have just a good idea. We also have a functional prototype. This is a Light Fury. We have it outside if you want to check it out later. It's a fully working electrical vertical takeoff landing aircraft. We did plenty of testing. The past years, like 2 years now in a row, we went out in the field, we tested, to make sure this aircraft is working safely. That's the key to really get the permission to operate somewhere, remote, also automatic. It needs to work, and you need to prove it. That's what we're going to do. Flight testing is always not just a very important part, it's also a fun part. I like to show this kind of footage every time. This is vertical, FPV footage of the aircraft somewhere in the empennage. Something you rarely see, but here you can see the control inputs of our pit loop. You can see the control inputs of some maneuvers which a remote pilot is indicating. And you see, especially in the beginning of the startup, right there, this enormous shaking. So it's also always a test of the stiffness of the aircraft. This is from the ground station. This is Night Fury 3. We have it also in the first first level here. You can see it. It's our competition-winning aircraft. It's actually a fantastic aircraft. It's super efficient, extremely lightweight, and also we developed it with a modular design, so we can use it for certain purposes, such as fire spotting. Just an idea, how could such a mission look like? This is 10 Lower Forest, together with Neunhofer and Erlenstegener Forest, and together it links to a forest area of 100 square kilometers. 10 Lower Forest is just 10 kilometers, but it's severely there are plenty of shells and ammunition in the ground, so this is why we need forest fire prediction in this area, because there is usually no passenger passing by in this area. It's not allowed to enter, and actually right now we have 60% of all fires reported is from people passing by. This is not working here. That's why we need something. We also have VC Airport and the highway, and with our mission, with our smart waypoint planning, we can cover all this area with just one flight of 50 kilometers. That means we just need one drone to cover 100 square kilometers. If you scale it up to German level, we just need 21 drones to cover all the inaccessible forest area. We don't want to just, we do more than just the detection itself. Once there is a detection and once there is the confirmation of the system, we cooperate with the fire brigades whilst they operate. Also, and for this reason, we need to make sure we don't interfere with, for example, police or Fliegerstaffel of any other emergency units. That's why we have other sensors on board, like LiDAR, camera, and ADS-B, just to detect other aircrafts and to avoid them when they operate. How do we do this? Once we have software and we have the sensors, and with a VTOL capability, that means we can stop mid-air. No other aircraft with wings can stop mid-air. We can just like park our drone when we say, okay, there's some obstacle. Some challenges we face, legal, in Germany, absolutely important. We need to make sure the aircraft is operating safely. This needs to be improved by LBA. We are working on this. It's a long process. But next year we want to make our first beyond line of sight mission. We need redundancy and safety in our powertrain and battery system, whatever. This is why power electronics is such a big thing here. Also for this application, we need communication. Long distance communication is always a mess when it comes to high altitudes. And we need to make sure the environment is not harming our system. What we need, cooperation. That's without cooperation, such a important and such a technical project is not possible. We have on the one hand side of Fraunhofer, which is an important partner, very good ideas. We have the FAU, since all the students coming from there. We have all the chairs, which we cooperate, many chairs which we cooperate with, but we also need partners. So if you have any ideas, if you want to work with us together, so just join us at the end of this conference and talk to us. We are super happy to find partners in industry. We are here in Fraunhofer. That's our location usually. I already mentioned we are here once on this conference and also in the basement, so just talk to us. If you don't make it today, or for the online audience, you might find us on some fairs like PETSIM, here AirTag. We have been last year, AACI, but also on 4th of November, Dies Academicus, we will also present our drone there. So thank you for your attention. Connect with us. This is, we are on Instagram, LinkedIn. Write us an email and more information on our website. Thank you very much.
You have the call to action. So first of all, congratulations on your achievements. This is really impressive. And my second question, when do you have time to study? Just kidding. You don't have to answer that. There are too many professors here. You have a question.
Hi. I was wondering if your market is based on inaccessible forests. That's how it's. So you were giving some ideas of how far that is in Germany. What about worldwide? I can imagine that there's an enormous amount of forest that is in the world. And how would you scale your startup with a global approach?
Yes, that's actually a very important thing. We don't focus only on inaccessible area, also on other, for example, private forest. 50% of German forest, for example, is private owned. We also focus on this, but also on European level. Once we have the legal permission to fly in Germany, we also automatically have the legal permission to fly in Europe. And Europe is the gate to the world.
Questions?
Congratulations, I'm very excited. So, first of all, an offer, if you look for a mid-range computer vision guy to help, I volunteer because I'm so excited. Once again, a great idea. Looking at your device, it looks some kind of unique, the quadcopter combined with wings. How is it with patents? Is this type of architecture new, the design new, and do you have the patents for your startup?
We don't have a patent on the whole concept. The concept is not new. We didn't invent this concept, we just use it properly.
That's progress.
That's the thing. Yeah, with all our experience, we developed subsystems, which might be patentable. That's not right now not our goal, but it might be some software aspect or some power electronics part, like battery management or something, which is patentable. But that's not the goal right now. It's more like experience and the database, which is Evolonic only at first. Yeah.
But please keep this intellectual property in mind, and keep in mind that also FAU provides support for students to set up the applications.
Okay. Yeah. Thank you.
Any more questions?
Hi, and thank you very much for your pitch. Very interesting. I'm sure that flying tests are extremely fun, and it is maybe the funnest part of your activity. But my question goes towards also the question of my colleagues. When thinking about scaling that up, so more forest and so on, have you thought also about some kind of digital strategy? I mean, the more EVTL you will have on the field, the less time you will have for testing, for real testing. So have you thought about replacing some of the testing with some kind of simulation or digital approach?
You mean prediction of fires?
No, I mean, for example, you mentioned flying tests, so I guess many of the tests were also to see if the airplane takes up and so on, and how it flies, and what is the distance that can be covered. So thinking about replacing some of the test with some kind of digital prediction.
Yes. Good, I got your question. Yes, we thought about kind of supporting our results by digital simulations and so on. There's on one hand side classical simulations when it comes to the development process, like aerodynamics, control theory simulations, but also like whole system, like mission control, or like if you have a failure, to think what will the aircraft do in case there's a failure, which we cannot do in the field because every time we need to sacrifice an aircraft, that's not possible. That's why there's also, for example, Siemens, a good idea which we thought about is digital twin. Create a digital twin means we can kind of produce, make a failure by ourselves, and then we can see what the aircraft might do in safe environment.
Maybe a question from my side. You have a great idea. You have a really impressive prototype. What do you need to create a viable business model? I think the questions went a bit in this direction already. So what's your vision? How do you commercialize this idea?
Yes, we need, first of all, we need support to make a safe aircraft. This is the technical aspect. And second, we need support and the willingness of politicians, of officials, of private owners to say this technology has potential and we need it as soon as possible. Because the users, which are the fire brigade, they want it. They really want it. Every time we present it, they say, okay, when can you deliver? But we need the permission on legal aspect and we need the willingness to invest in such a theory, such a technology, because it has more like the social character and not the business character as in first places, especially not in Germany, because the damage in economic standards is not high enough to say, okay, this is really worth an invest, but it's supposed to be a social invest. That's what we kind of need, this kind of willingness and support from politics and also industry.
Thank you very much. You know where Zollhof is, you know where to find us. Yeah. So if you would like to talk about further business cases, we are there for you. Thank you so much.
Thank you very much. Thank you for your time.
Next up is Ceus. So I would like to invite you on stage. And I think we had a little change in the presenting person. So maybe first you introduce yourself and then you can pitch.
Yes, so my CEO, Raphael Chacon, unfortunately isn't available today. So I had to step in on quite short notice. My name is Adrian Foster and my position is actually more engineer. I'm an application engineer, development engineer and parts. I do software as well in some parts. So it is with a smaller startup, so you do interdisciplinary work. So, well, here you see a logo and actually a fun fact to make a connection to the previous presentation. The bike you see there stems from a project where we worked on when we were students as well on the Fraunhofer Institute. It's basically a predecessor to the drone project. And that's it with the company. This company itself is a spin-off from the Fraunhofer IESB. So my CEO worked here and then took a project and took it basically out to industrial to make a working project and to sell it. And we focus on power electronics as we, well, do come out of the power electronic background. And in our rooms or bureaus and laboratory in the Medical Valley Center, this is the picture you see here. We have a little bit test facilities for our electronic development. So basically we design the electronics and we can test as well. We do some tests with batteries as well. And we dabbled, let's say, in UHF RFID, where we try to use commercial available hardware to 3D localize things. Yes, so our work is we work with industry partners. We work as like design contractors, and we do R&D. And we are together with the FAU with Professor Merz chair the LEE. We are in youth research projects as well. And on the picture you see as well partners from where we have a network. So we are in a H2 network and an automation and yes. And well, basically the homepage. You always need a homepage. So what is Ceus? Ceus is basically, so the name is a clever pun on the Greek god with the lightning to connect to the power electronics. Under our roof, let's say, we have the development process and the product development process, we combine interdisciplinary work there, from simulations, electro and mechanical integration, which is a great part, product design as well. And for the product development, we can do testing and qualification, as well as be a partner in testing and qualification. We have a little bit of a lab with manufacturing, although this is strictly down to prototypes, our own prototypes. So we don't manufacture products in great numbers, but we manufacture our own prototypes so that we can test them. So basically to have a shorter time in this process. So when we come to the product design, there is basically, as big as the company gets, the more divided basically the pillars of the product development are. So you have basically software development, you have hardware development, and you have the simulation and development department, as well as mechanical design. And all of these are obviously valuable and needed parts of the development process, but the problem is the bigger it gets, that's our experience, the bigger the difference or the language gap, the communication gap between the single department is. And so we try to bring that all together, or to, as service, have the interface communication for this. And I want to show this on a practical example on the next slide here. You see DC-DC converter, which stems from the LEE chair, or is in cooperation with the LEE chair, who do the smart development of the electronics, of the design of the topologies, and we help them there with integration and the interfacing of a different part, and with testing. And this is from the EU research project Progresses. And well, basically here I have some facts for you here. There's a bidirectional converter with a voltage range up to 1000 volts, and application as a modular unit for DC fast charging up to 400 kilowatts. The main challenges in projects like these, where you have electrical engineering, simulation, and mechanical engineering, as I talked before, is the interface between the different groups. So the combination of mechanical properties, like tolerances. So I myself, I'm an electrical engineer. So when I see high voltage applications, I look at what clearances I need for so not to have errors on the circuit boards, and the mechanical engineer sees tolerances in when the actual device shifts. So basically, I would, in this example, make a free space around a hole for a screw, and probably not take into account the mechanical tolerance, and so it could shift, and the head of the screw could basically produce an error. That's a problem that we, as an interdisciplinary team, from the backgrounds of mechanical engineering, simulation, and electrical in engineering, in a small team on a small space, try to avoid and try to make better in the case that we are working closely, basically on the same space, and some persons have multiple aspects to work on. So basically, if I take myself as an example, I design hardware, so the circuit and the layout, and as well do C programming on the controllers for embedded programming. So I've got the interface to software engineers for applications. Yeah, that's what basically that's the interdisciplinary. This is really the focus on applications like this. So, and therefore, the whole thing, the topic that we try to address here, or try to address when we work with our customers, is language and language not only in the sense of English and German basically here, but language is the most basic means for most of us of communicating with each other, so understanding each other. And that's the point where interdisciplinary projects show problems most of the time. In the technical space, language can also mean standards, norms, and documents like this, or interface descriptions. So you need to be clear where you interface to your neighbors, and this is a point where we specialize as well. Okay, so this was a short introduction on our company. Do you have any questions that I can answer?
Thank you very much. Do you have any questions?
Yes.
Oh.
Okay, only to get it right. That means you are something like, let's say, engineering company.
Yes.
Which is working in interdisciplinary teams.
Yes, with the focus on power electronics. Yes.
Okay. Okay. Thank you.
Along these lines, are you just a service company giving a service for customers who want to develop some products, or you have own products?
We do have own products. The whole company started with with a product that was taken out of the research and development process on the Fraunhofer. Then there was a spin-off that started. This is basically a small 1 kilowatt-hour battery system that is used in autonomous desks. So you have a desk where there's no cable to the ground. You have a desk where all your laptop is connected, and your screens, everything is connected to a power box basically. And we did the first product was the accumulator, the battery, that the employee basically takes on the beginning of his day, puts in his desk, and can work without having a power cord. The idea behind it being like creative bureaus for development processes, where you have larger areas with mixing teams basically. So you have a lot of people developing or having creative ideas, and they want to meet in different groups in the area, and that's where the idea came from, that you have the autonomous desks, and then you basically push like your little groups together, like you want to work for this day, this afternoon, this week, this month. Exactly. Then we have like expanding on the same idea, an outdoor power bank basically with around 700 watt hours, which was used in a sail around in the Vendée Globe, which is extreme sports single-hand sailing. They had one of our batteries on board, one of them, and the DLRG, the rescue service part in Fürth, they're using this for a boat if they are on the water and need to power small stuff. Yeah.
Thank you very much for the answers. Unfortunately, we don't have time for more questions, but you are staying a bit longer, I guess, so please feel free to approach, and then you can clarify the remaining questions if there is any. Thank you so much.
Thank you.
Thank you. Last but not least, Powerlies, which is a test laboratory for electric assemblies. And Martin, the stage is yours. Here is your presenter.
Okay, thanks for a kindly introduction. Dear audience, it's a pleasure to present my company, the Powerlies company, today. My name is Martin Muckelbauer. I'm head of this company, and before I worked several years at the University of Erlangen at the Institute of Professor Franke, Institute for Factory Automation and Production Systems. Yes, as we heard, we are a service provider for electronic components. We are a test lab and with a focus of, on power electronics. Yes, and first I want to begin with a map we have partially seen today in a clustered way, the transformation to the all-electric society. We are in the middle of this transformation, and we've already heard power electronic is everywhere within this grid. So I just marked up some single points of this, which we see fields for activities of our companies. So yeah, we are very positive for the future to have a lot of workload. So first, I want to begin with the transformation also from pure silicon base to silicon carbon semiconductors. So we've already heard the advantages. They are very clear: higher efficiency, up to 66% lower losses, higher power density, longer ranges, reduced system dimensions, optimized housing technology, faster charging times, or a significant cost reduction. Yes, but the semiconductor is not all. Without the interconnection to the power module, it's nothing. And so the new technologies that are required are completely full of new materials, completely new interconnection technologies, interconnection processes, and so our customers build up completely new modules that have to be tested. But how to test a completely new module? And so several years ago, the ECPE, the European Cluster for Power Electronics, launched a guideline that was set up from former standards and guidelines. It's so-called the AQG, the Automotive Quality Guideline. It's specialized for power electronics in the automotive sector. This is also the field we are active currently. And yeah, it's a framework, I would say. It's not a standard. So with the creation of this guideline, several interests hit to another. And so a framework for testing was created. But in the future, there is much more precise standardization for test specifications needed. And so we try to give several supports to our customers. First, I would say, based on the automotive guideline, our customers often don't know what they want. The demand is unclear, the specifications doesn't exist, and so we work out a very precise test specification framework, and we test the power modules from our customers with active tests. Probably you know, active power cycling, and we measure our modules with intermediate precise tests, for example, for thermal impedance, or also in a transient way, the thermal impedance. And with these results, we can do meaningful, give meaningful answers for failure modes inside. We also do passive testing, thermal, mechanical, and we combine the tests. To combine it is very hard. We saw when we look into the companies of our customers, it's a thing of waiting mostly. They have modules and the test field is completely run out with operating modules, and if there are intermediate tests necessary, it completely collapsed. And this is our core competence, to run the tests very tight, one to each other, and to give a very quick response to our customers. And we already heard the time is running. Product life cycles are getting shorter and shorter, and so the development of power modules is is a phase that takes very long. So these are tests. Sometimes we speak about months that one test lasts. So we combine active and passive methods. We use accelerated test methods, but with our testing system, we help to accelerate also the development of our customers. We have a high significance of our tests, and the test results enable the development of robust and reliable power modules. And another thing is we develop our tests to need less energy. So some of these tests are very energy intensive tests, and so we see the requirements that we do developments with our suppliers to create test equipment and test machines that is much more resource efficient. Yeah, now I just want to have a few on the Roland Berger megatrends that will determine the future developments. And we see in three of them the environment and resources section, the economic and business section, and the technology and innovation sections. Fields we can take part and make a contribution and create value. Yeah, it's a quite bright field. We are active with our company. So we have heard that collaboration is everything. So the Powerlize company is part of the incubator funded by the city of Nuremberg. We are located on the AEG campus in Nuremberg, and our core partners are also the FAU, especially the factory automation and production systems chair of Professor Franke, and we are in the network of 3D MID, and of course the ECPE network probably will arise next year. So thank you very much for your attention. If there are any questions, don't hesitate to ask. No?
Thank you. I would actually have the first question to you, because today we touched upon the complexity of supply chain and value chain in this industry, but we didn't really talk about the last 3 years. It's a very turbulent time, and how does this affect you? How do you cope with the turbulence of the supply chain that we all experience?
Yes, when we talk about semiconductors, it was a problem for us because our customers build up modules with semiconductors. Without semiconductors, if semiconductor is not available, it's very rare, then we don't have test vehicles to test, and this is a problem. But also semiconductors are built in the machines we use. So we have heard about companies, they have products, they have IT. We have assets. It's very intensive with equipment, but currently it's also hard to get equipment. So it's very turbulent, but everywhere are solutions. No? Yeah, you have very dynamic, and yeah, so yes, this is a problem. And also it was a problem from the automotive industry. So 2 years ago, at the shutdown, it was hard to get a service provider jobs from bigger companies. So our core customers are first tiers for the automotive industry. It's clear. So in the Nuremberg region, we have a lot of strong automotive suppliers. So it's a very good environment for our business, I think. Yes.
Thank you. We have time for one question, and then you are also staying, I guess, so you can talk to Martin later on.
Thanks a lot. I like the first picture you showed with the overview of your
activities. It's not surprising as the source is Siemens, but on that there was MindSphere, the IoT solution from Siemens. Now I'm leading the sales for MindSphere in EMEA, therefore it was very interesting for me. And considering that, I think we recently found a sweet spot for our offering in the market, which are innovative, high innovative startups that address sustainability solutions like power storage or renewable energy sources and else. They all use semiconductors, and what they are currently doing now is to connect their assets in the field, playing back the data. Now, what I would be wondering if you as a company would be interested in the data from the field of these companies, if you could then even improve your test procedures, not only in advance, but also during the operation of these activities, and if this kind of ecosystem approach, using an IoT platform, leveraging your customers and yourself and your know-how, if that would be a valuable way to go forward.
Perfect, yeah, that sounds very interesting, and I think at the basic, we work with hardware, but also automation, software, data are very big topics in our field, and we also correspond with our customers. Mostly the data from the field has our customers, but we talk to each other and we discuss also the failure mode, because with our new power electronic build-ups that are more robust and have a quite much more lifetime, it's harder to test, so we need harsher test environments, but the aim is to realize an equivalent to the failure modes from the field. So it's very important to get failure modes from the field and data to applicate it in accelerated testing.
So let's talk afterwards.
Thank you very much. Yeah.
Great, thank you very much for the pitch.
Thanks.
And with that, I give back the stage to you.
Thank you.
And thank you for your great questions and for your...
Thank you very much. I think it was very interesting. We had a lot of different startups and different concepts. We already talked about the foundation of all the research of new ideas, etc. And that's why we have a new study program at our Department of Engineering. It's called Electromobility ACES. And Dr. Oliver Kreis will hopefully explain what this new study program will bring to the ecosystem.
Okay, thank you very much for the introduction. Well, today we heard a lot of research and innovation. And we heard already that we have a lack of competent engineers in this area. And to lower this lack, to give more engineers to the industry and to the research, we introduced a new study program named E-Mobility ACES at our School of Engineering here. And we started right now in this winter semester. And I will give you a very, very short pitch presentation about this, because I think you all want to go for lunch and we are somewhat over the time, so make it very short, so maybe that we have a little bit more time for some questions, and we'll be glad if you have a small discussion. Well, we called it E-Mobility ACES. Why ACES? Because we thought e-mobility is a very hot topic, but today already you could buy about 50 different electrical cars in the stores, or I said you could buy them if the industry could deliver them. But it's state of the art, but it doesn't. There's not the view in the future. So we say we must make more. We are the university. We must do the things that may come in the industry in 10 years from now. And so we call it E-Mobility ACES. And ACES stands for the 4 majors that we identified. That is AI and autonomous driving. That is connectivity, e-powertrain, and sustainable. And this is according to a McKinsey survey from 2019, where McKinsey identified these 4 megatrends in mobility. And to give you a short view about this, our students will choose 2 of these majors in their study program. For example, here in AI autonomous driving, for example, you see here how a car sees the street. Computer science, autonomous, of course, we need all the sensors and all of this stuff. And I'm very happy. It was very funny for me. Companies like Tesla, for years, they promoted their autopilot. But it was a German company who offered the worldwide first level 3 autonomous driving here, Mercedes, and soon BMW, Audi, Volkswagen will follow. But it's very nice for me to see that Germany is still on the top of the high-tech here in automated driving. Then in connectivity, this refers, let's say, I'm a mechanical engineer, so I say that is low courage and high courage. Yeah. So communication here, like car-to-car communication, sensors, automated, but also things like smart grids. If you think at 18 o'clock, millions of electrical cars will come home, drive in the garage, and all people start loading their cars. How should this work? So you need load balancing, and there we have a link to our conference here with power electronics. So smart grids, charge management, for example. Then we have the e-powertrain, defined very widely from our side. So from the battery to the tire, that is the e-powertrain for us. So yeah, very strong electrical engineering and mechanical engineering, power electronics in vehicles, or the all production technology, like here a view of Volkswagen for the ID.3. And the fourth major is sustainability. So sustainable mobility and sustainable production technology, meaning things like efficiency in fabrication, or let's say hydrogen. How can you produce this efficiently and ecologically? How can you store this? And of course, shared mobility. We will not make all our trips with electrical cars. Maybe it's much smarter to choose between, let's say, electrical trains, and then just drive the last kilometers electrically with a car or with an e-scooter, for example. So these are the four majors, and there we integrate the competencies of our Faculty of Engineering here. And that was extremely attractive for our students. While we had our takeoff this winter semester here, just a vision, maybe in some years from now on you can fly from Nuremberg Airport electrically, hopefully. And we had an extremely successfully takeoff in the master program with 430 master students starting this and about 50 bachelor students starting this. So that is already the end of my presentation, and I thank you very much for your attention. And would be happy if we could have a small discussion before the lunch.
Are there any questions?
Hello, the 4 ACEs you mentioned, they are spread across bachelor and master, or are they divided into? So, for example, if you're talking about powertrain, is powertrain one of the ACEs that is been studied in bachelor and master? It's in both?
The majors are in both, in the bachelor and the master program. Of course, in the bachelor program, in the first 4 semesters, you need all the basics. You need mechanical engineering, electrical engineering, computer science, and then you have the majors in the 5th and 6th semester. In the master, the students may start directly from the first semester on in 2 of these majors. Yeah, you're welcome.
Maybe we have questions later, because I hope you stay for lunch.
Okay.
So all the students who are here, maybe you're interested in changing your subject to this new study program.
Yes, really. If you have your bachelor in mechanical or electrical engineering, you're open to apply for our master program here. Yeah.
Because I think it's very interesting. Okay, so can I go to the center?
Thank you.
Okay, so I'm also going to do this very quickly. Before we close this event, we have 2 upcoming events. We have the Fem Tech Talk, Entrepreneurship X Female Power, and we have also the Siemens Tech for Sustainability Campaign 2023. And thank you very much to all the speakers we had here today. Thank you for your time, Dr. Roland Busch and Dr. Joachim Hornegger. It was very interesting and very insightful. I would like to invite you to lunch later, and we have also at 13:45 some lab tours. I think there are 4 parallel lab tours. It's the first come, first serve principle, so we have, I think, 15 places for each group. The lab tours start downstairs, so you can just come to the desk and register for the tour you're interested in. Thank you very much.